Chapter 27 of The Ocean of Air, Meteorology for Beginners. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by Elizabeth Miles. The Ocean of Air, Meteorology for Beginners by Agnes GIBERNE. Thunder and Lightning. Chapter 27, Thunder and Lightning. One of the most wonderful and awe-compelling sights to be seen in our ocean of air is a brilliant flash of lightning with its attendant roar of sound. Severe cyclones, whether temperate or tropical, besides bringing fierce winds, heavy rain, and furious ocean waves, are usually accompanied by lightning and thunder. The thunder and lightning of the tropics are such as we never hear or see in our island home, yet even in England, death from a lightning flash is no unheard of event. Indeed, taking them all round, the cyclonic thunderstorms of temperate climates and of cold seasons are really more dangerous than the heat thunderstorms of the tropics and of very hot summers. Though the lightning may seem less severe, the clouds lie lower down, and the passage of an electric spark, not merely from cloud to cloud, but from a cloud to the earth, is more common. Two kinds of lightning are commonly known to us: zigzag or forked lightning, and sheet or summer lightning. The second of these is in most cases only a reflection of the first. When we look at the flash itself, we call it zigzag or forked lightning. When we look at the reflection of that flash on the clouds and in the air, we call it sheet lightning. Summer lightning is often the faint reflection from a storm, either too far off, too low down beyond the horizon, or too high up above intervening clouds for us to see the forked flashes themselves. Occasional instances of summer lightning cannot, however, be thus explained. There is a curious vagueness in the minds of people generally as to the duration of a lightning flash. A statement was lately made in the leading tale of a well-known serial that a certain flash lasted fully half a minute. A flash really lasts no more than the merest fraction of a second. Some say the 10,000th, some say the millionth of a second. None know exactly. No doubt it seems to continue longer, since the retina of the eye keeps for a brief space any impression which falls upon it. This may be shown with the help of a spinning top. If a piece of paper full of large holes is made to whirl with the top, it will appear to the eye like a continuous sheet of paper. The holes in the paper are, so to speak, filled up by the picture of the paper between the holes remaining on the retina as the holes rush by. So though the actual flash of lightning is over with almost unimaginable rapidity, its radiance lingers on the retina of the eye for a much larger part of a second, but a half a minute, never. The most rapidly moving or whirling bodies ever seen on Earth always appear perfectly still when seen by the light of a lightning flash. This is a sure proof of its extreme speed. A good many thunderstorms have already been described in past ages under other names. Hailstorms, cyclones, tornadoes, hurricanes, severe gales, even violent snowstorms are more or less accompanied by thunder and lightning. From time to time, individuals are struck and either injured or killed, but such accidents are comparatively rare. Some years ago, a gentleman and lady were staying in Wales, not far from Cardigan, when a heavy storm took place at night. The lightning struck the house, and the very bed on which they lay was burned, yet they escaped with their lives. At another time, Derbyshire was visited by a severe storm. The lightning struck a certain grange, passing downwards into a room where tea was going on. The master of the house was killed on the spot, while his wife and a servant were both hurt. But such instances as these have to be selected from among thousands of cases where no material damage is done. We come now to the question, what is a lightning flash? It is the visible passing of electricity from one cloud to another, from a cloud to the earth, or from the earth to a cloud. And what is electricity? For a long while it was believed to be an extremely thin fluid creeping into and flowing through other substances. Some held that it was a single fluid acting in two modes, some that it consisted of two different fluids. The idea of electricity being a fluid is now laid aside. It is believed to be not a fluid, but one of nature's forces or forms of energy, acting, in the case of thunder, in and through the atmosphere. We continue, however, to speak of the electric fluid. The term is a convenient one, and it has grown into general use so as not to be easily given up. Globular lightning, so called, is still much of a mystery. There can be no doubt about the actual phenomenon, but people are apt, when it appears, to be too much startled or agitated for calm observation. It takes, usually, the shape of a bright ball of fire traveling deliberately through the air and exploding with a crash. In size, it is said to vary from a few inches to 2 or even 3 feet in diameter. One such ball was seen in Paris descending from the sky, and when it burst, forked flashes seemed to dart from it. Forked flashes might, however, easily come from friction, like the excitement of electricity in the aurora. Another was seen in England, rising from the ground and zigzagging upwards till it passed into a dark cloud. A third was seen in Ireland, floating leisurely over the ground, now and then dipping into the boggy soil, where each time it dug a deep hole or trench and at length burying itself in the earth. It seems probable that a fireball partakes rather of the nature of a meteorite than of a lightning flash. If so, it does not come under the head of electricity. The phenomenon altogether is a matter for doubt. End of chapter 27.
Chapter 28 of The Ocean of Air, Meteorology for Beginners. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by Logan Lorenz. The Ocean of Air, Meteorology for Beginners by Agnes GIBERNE. Electricity and Magnetism. The whole Earth is full of electricity, and the entire ocean of air is more or less overflowing with it. But for the perpetual presence and influence of this force, our atmosphere would be different indeed from what it is now. A chapter may well be given to explaining a little about electricity and the twin power, magnetism. About 600 years BC, somebody discovered that if a piece of amber were rubbed, and were then held near small scraps of a light substance, it would attract the scraps, making them spring up and cling to itself. Before being rubbed, the amber did nothing of the kind. Jet was proved to possess the same power, and there discovery stopped. People were not, in those days, very keen after scientific knowledge, or they would hardly have waited through so many centuries following, through the days of early Christianity and through the Dark Ages, till the time of Queen Elizabeth, before taking another step forward. Though only amber and jet were thus far known to possess this curious gift of attraction, when rubbed, the characteristic was found to belong to a great many substances. To sealing wax, for instance, to glass, diamond, sapphire, and gutta percha. Any of these, if excited by friction and warmth, were seen to attract light bodies, sometimes at a distance of several inches, and some of them would shine in the dark. Such substances received the name of electrics at the beginning of the 17th century, while the mysterious power at work was called electricity. The word springs from electron, which is the Greek for amber. Nothing is easier than in a small way to try this attractive power for yourself. If you rub a stick of sealing wax well with silk or flannel or fur, and hold the rubbed end near a little heap of very tiny paper cuttings, some of the latter will at once spring up and cling to the sealing wax. Electrified substances do not always attract other substances. Sometimes they repel or drive them away. For there are two kinds or forms of electricity, positive and negative. When a body is electrified, it is always in one of two different ways. Try another experiment. Hang a light, small ball of cork by a silk thread, then rub a piece of sealing wax, and hold the rubbed or excited end near the ball. At first the ball will be attracted towards the sealing wax, but presently it will move away, being repelled. The sealing wax and the cork ball are in the beginning differently electrified, one with positive, the other with negative, electricity. Then they mutually draw together, or would do so if both were equally free to move. But when each has given over to the other some of its own electricity, the two become electrified alike. Therefore, each drives the other away, and they fly apart, or would do so if equally free. The ball alone being free, alone moves. So if one body electrified with positive electricity comes near another body electrified with negative electricity, each attracts the other, and if free to move, they draw closer together. It seems as if the electricity of the one desired to flow into and mix itself with the electricity of the other. But when two bodies are near together, both electrified with positive or both with negative electricity, no such desire is shown. On the contrary, each seems anxious to get away from the other. If electricity were a fluid like water, we should say that it flowed from one substance to another, in the struggle to keep its own level. If electricity were a fluid like air, we should say that it flowed to and fro, in the struggle to keep its balance or equilibrium. Since it is neither, those terms are perhaps hardly allowable. Yet there is in electricity, as in the said fluids, an incessant effort after something like balance, after something like equality, after a perfect adjustment, and a fair distribution of itself everywhere. Although electricity cannot be considered a fluid, it behaves in many respects very like a fluid. It is indeed caused to appear, or generated, by rubbing, which is not the case with any known fluid. But generated does not necessarily mean made. Electricity seems to be in all bodies, hidden away, only not apparent to us, till its quiet is disturbed by friction or other causes. The manner in which it flows from one to another part of a substance, or from one body into another, is very like the action of a fluid. Again, there seem to be definite quantities of it everywhere. Electricity cannot spread and increase like flame. When some flows out of a body, less remains behind. Every time one substance rubs or even touches another, a flow of electricity takes place one way, if not both ways, though without exhibiting what is called electrical action. So the quantity present in any one body is always varying. But here we come upon a marked difference between different substances. Some do very easily show electrical action. You have seen how sealing wax, when rubbed, immediately attracts or repels, and it is the same with all so-called electrics. Many substances, such as gold and silver, marble and pearl, iron, and indeed all metals, may be held in the hand and rubbed to any extent without producing the same result. In past days, they used to be called non-electrics because it was supposed they could not be electrified. Now that term is dropped, for when a non-electric, such as silver, is rubbed, we know that electricity is generated just as fast as when an electric, such as sealing wax, is rubbed. The difference consists not in the amount of electricity, but in the ease with which the metal conducts it away, compared to the resistance offered by the sealing wax. So now we talk not of electrics and non-electrics, but of good conductors and bad conductors. Iron is a good conductor, and so is the human body. If you hold a lump of iron in your hand and rub as hard as you will, you cannot make it attract or repel, for just so fast as the electricity is generated, it pours away into your hand, up your arm, and down your body into the ground. But suppose you fasten the lump of iron upon a glass support and do not touch it with your hand. Glass being a bad conductor, communication with the ground is thus cut off. If the iron now be rubbed, it will attract and repel like excited sealing wax. There is still, however, a difference between the iron and the sealing wax. When a stick of sealing wax is electrified by rubbing, all the electricity remains or seems to remain on the outside, just where it has been generated. It does not flow around and along the stick to other parts. When the iron is electrified, being cut off from the ground by a glass support, the electricity flows freely over its whole surface, though unable to get any farther. In both these cases, the store of electricity on the surface is spoken of as a charge, and the iron or sealing wax is said to be charged. If the stored electricity passes away from either, it is then said to be discharged. But when the electric stream flows freely along a good conductor, as for instance along a wire, it is characterized as an electric current. Now, water is a good conductor. An electric wire laid under the ocean has to be carefully guarded from contact with the surrounding water, or the electric message, flashed from one country to another, would all leak away into the ocean by the way. Dry air, at least in the lower regions of the air ocean, is a bad conductor. If it were not so, no good conductor could ever be electrified by being fastened upon a bad conductor, because even though cut off from earth and other substances, it would still be touched on all sides by air, and all its electricity would flow away into the atmosphere. Dry air acts in some degree like the glass support, and imprisons the electricity. Floating vapor in the air, however, helps to give right of way to electric currents, and prevents air from being a thoroughly bad conductor. In very damp weather, air becomes a much better conductor, and on such days, electrical experiments are apt to prove a failure because of the quick passing away of electricity into the vapor-laden air. The damper air is, the better it conducts. On the other hand, the denser air is, the worse it conducts. Both these facts tell upon the lower layers of the air ocean, which are alike more damp and more dense than high layers. Air may be said to act generally as an insulator or bad conductor, but only to a certain extent. If an excited stick of sealing wax or glass is left in the open air, it gradually loses its little charge. The store of electricity on its surface leaks away into the air, faster or more slowly, according to whether the atmosphere is damp or dry. When two clouds draw near together, one charged with positive and the other with negative electricity, there is a strong attraction between the two. In either cloud, the electric stream flows, converging towards one part, that part of the cloud which lies nearest to the other cloud. Sometimes the state of the atmosphere will allow a quiet and gentle restoration of electrical balance. If where the clouds lie, the air is damp enough and not too dense, a current may make its way from one cloud to the other without anybody on Earth being aware of it. But if the air is very dry, it resolutely resists the passage of the current. Things go on getting worse and worse, till at length they have to be righted, notwithstanding all opposition. If the electric current may not flow peacefully, it will end by forcing its way fiercely. Then the culmination comes. An enormous spark of electricity leaps from cloud to cloud with a crackling roar. Thunder, as we hear it, comes to us commonly softened in some degree by distance, and lengthened out by rolling echoes. Sometimes when a storm takes place close overhead, we hear for once the actual metallic crash unsoftened. An electric spark caused to pass from point to point of an electric machine, leaping through only an inch or two of space, will make a noise by no means contemptible. No wonder the great lightning spark, rushing through miles of space, sometimes as much as 8 or 10 miles, should shake the very earth with its peal. The sound is caused by the electric current forcing its way through the fiercely opposing air. In the struggle, it turns to and fro, following a zigzag path. Like a river, it flows where it finds least resistance. When an electric current passes through a resisting substance, there is always great consequent heat. The air, under sudden and tremendous heat, expands instantaneously to an enormous extent, and contracts again as rapidly the moment the flash has gone by. An immense rush and pressure of air particles are thus caused. The crackling thunder crash is the fruit of the furious air resistance, air expansion, and air contraction. Footnote: a discharge of electricity through a non-conductor, such as a lightning spark passing through air, is called a disruptive discharge. Such a discharge is usually accompanied by light, heat, noise, etc. End footnote. A lightning flash travels at the rate of about 290,000 miles in a second, half as fast again as the speed of light. Lightning conductors are often placed near high buildings. The object is to offer a safe and easy path to the electric current from the clouds into the earth, safe as regards mankind, easy as regards the lightning. Electricity will always take the easiest path which offers itself. A conductor is made of metal, which allows free flow to the current. It ought to end in a damp layer of earth, where the current can spread itself about harmlessly. One can hardly speak of lightning conductors without an allusion to Dr. Benjamin Franklin of Pennsylvania, to whose experiments the world still owes much. He it was who, about 1750, first sent a kite aloft during a thunderstorm, rightly calculating that electricity from the charged clouds would pass down the string. A key was tied to the latter within his reach, and when he touched the key with his knuckles, he drew from it a bright electric spark. Such experiments meant, and must always mean, no little danger to the experimenter. Franklin escaped unhurt, but others have been less fortunate. About the middle of the 18th century, a melancholy event took place. Professor Reckman of St. Petersburg had put up on his house an iron rod to collect the electricity of storms, and he had below an electrometer to measure the amount collected. One day, during a severe storm, he was carefully watching the electrometer, bending his head to about a foot distant from it, when a loud peal of thunder sounded. Instantly, a bluish ball of fire, as large as a man's fist, leaped from the iron rod to the professor's head, with a report like that of a pistol. Reckman fell dead, and his half-stunned companion was covered with red-hot bits of metal wire. Electricity and magnetism are commonly spoken of together. They are in many respects alike, yet the two are not the same. The lodestone was known in early days as a magnet, having a power of attracting to itself filings of iron or steel. But its singular characteristic of always pointing north and south, when so suspended as to have free movement, was not found out till about the 11th century. If iron or steel are rubbed on a lodestone, they gain the same powers. Magnets to any extent can thus be manufactured. Attraction and repulsion are connected no less with magnetism than with electricity. There seem to be two kinds of magnetism, or at least two kinds of magnetic poles. A magnet has always two poles, each different from the other. If a magnet is broken in half, each half at once has its two different poles. No one magnet has ever two poles of the same kind. The one pole attracts, while the other repels. The one points only north, and the other points only south. Take a magnet and hold each pole of it in turn near the north-pointing end of the needle in a compass, then do the same with the south-pointing end. You will find that one pole of the magnet attracts, while the other repels the north-pointing needle. But with the south-pointing needle, you will find the reverse. It is attracted by that pole of the magnet which repelled the north needle end, and repelled by that pole which attracted the north needle end. In fact, the rule here is much the same as in electrical action and repulsion. Magnetic poles, when alike in kind, repel one another. When unlike in kind, they attract one another. All this is very curious, very easy to see and test for ourselves, and very difficult to understand. There is a great deal in magnetism which nobody does understand as yet. One clue to further researches has been obtained of late years. This is, that the Earth itself is a huge magnet, with north and south magnetic poles, not far from the north and south poles of geography. Probably the Sun is another and most enormous magnet. It may be that a clue lies here for the future, as to the real nature of the mighty force of gravitation. Iron is more easily magnetized by rubbing with a lodestone than steel, and as a natural consequence, it is also more easily demagnetized. As a writer says, it is harder to get the magnetism into steel than into iron, and it is harder to get the magnetism out of steel than out of iron, for the steel retains the magnetism once put into it. Just what one would expect. As we saw in the case of water and solid ground gaining and parting with heat, that which is most easily taken in is also most easily lost, and vice versa. The attracting and repelling powers of a magnet will act through paper or wood, through glass or brass, through fire or water, but not through a screen of iron or steel. The iron and steel themselves attract the magnet so as to interfere with its powers over anything beyond them. For a long while, the fluid theory was used to explain magnetism. That theory is now given up. Whatever magnetism may be, a fluid it is not. The term is still employed, but merely as a convenience. Magnetism, like electricity, is held to be one of nature's forces, not in any sense one of nature's substances. Side by side with the marked resemblances between these twin forces, there are marked differences, such for instance as the following. When electricity passes from one body into another, a certain amount of the fluid is gone, and less remains behind. But when a magnet is rubbed on a lump of iron, magnetism passes into the iron, and apparently just as much remains behind in the magnet as was there before. A bar of iron or steel may be magnetized through being touched or rubbed by a lodestone or a steel magnet. This, however, is not the only mode. If no lesser permanent magnets are at hand, the biggest magnet of all within reach, the Earth itself, may be used. An iron bar placed upright for a long enough period gains magnetism out of the Earth. Moreover, heating and cooling under certain conditions may have the same effect. A steel bar, made red hot, then allowed to cool, while lying nearly north and south or in the magnetic meridian, is found to be magnetized. If it lie east and west, it is not magnetized. A more vigorous mode of magnetizing than any of the above is through a powerful current of electricity, borne continuously by spiral wires round iron or steel bars. Here again we see the close connection of the twin forces, a stream of electricity being actually converted into, or at least the direct cause of, magnetism. This magnoelectric union has been carried out to a wonderful extent with marvelous results in the electric lighting machines of our days. Passing mention must be made of the aurora borealis, a glimpse of which is sometimes vouchsafed to us so far south as in England, though it is in the icy regions of the north that the sight is seen in all its splendor. A certain observer belonging to a scientific expedition describes some of the wonderful and rapid changes noted in a single display. Rays of brilliant white shot over the firmament, lengthening, then dying out, to be followed by another spreading group of fan-like rays. Then golden waving draperies seemed to float and fold one over another. An arc of deep red contrasted with a segment of black, and a shining fan widened through the northern sky, rising gently upward. Overhead, its rays joined into the shape of a crown, and from the crown sprang radiant jets of light and color. Blue and green, yellow and red, quivering streamers of every hue helped to turn the sky into a cupola of fire, and presently the whole faded quietly, leaving only the stars twinkling in the dark night. The light of a bright aurora is so clear that small print has been read by it. The height of the aurora rays is believed to be from about 30 to over 100 miles above Earth's surface. The aurora is probably in some measure due to, or at least connected with, electrical and magnetic forces. It is certainly accompanied by magnetic disturbance. A new theory has, however, lately sprung into existence to account more fully for the northern display. Higher levels of the air ocean are believed to be filled with interminable clouds of meteoric dust, that is, of the material of which meteorites are made, floating as extremely fine dust. These clouds of dust incessantly receive fresh additions, as day by day millions of meteorites enter our atmosphere from the vast beyond, and there must also be an incessant tendency of the dust to descend, however slowly, earthward. If this be so, one would expect to find traces of meteoric dust upon Earth's surface or in the sea. It is a remarkable and suggestive fact that in the Challenger expedition, dust grains, or nodules, were dredged up from the ocean bottom, having every appearance of meteoric origin. The searching test of the spectroscope showed this dust to be one in nature with the dust which enters our atmosphere from distant space. And the same test applied to the light of the aurora revealed that the spectrum of the aurora and the spectrum of the meteoric dust are practically the same. It is now therefore believed that the aurora display is, at least in a great measure, due to abundant supplies of this dust in upper air levels, ignited in particular circumstances by friction with the air, and acted upon by electricity. How far the electricity is generated by the said friction is another question. End of chapter 28.
Chapter 29 of The Ocean of Air, Meteorology for Beginners. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by Giordano. The Ocean of Air. Meteorology for Beginners by Agnes GIBERNE. Heat. Much has been said from time to time about the part played in the ocean of air by heat. A few pages about heat and its modes of action may not be uninteresting. When we speak of a thing being hot or cold, we mean hot or cold as compared with something else, generally with the surrounding atmosphere. That which one person calls hot, another calls cold, and what seems hot to us at one time seems cold at another. It is all a question of comparison. The true temperature of a body can only be known by the thermometer, not through touch. The hand can merely feel that a substance is more or less warm than itself. Since a hand is always changing its own degree of warmth, it can be no fair standard for measuring the warmth of other bodies. Some substances gain and lose their heat much more readily than some others. Iron takes in and gives out heat faster than wood. If you have a lump of warm iron and a piece of warm wood, both just the same in degree, the iron will feel hotter to your hand. It gives over heat to your hand more quickly than the wood does. But if the iron and wood are both cold, still alike in degree, the iron will be coldest to your hand. It takes in heat, robbing your hand for the purpose, more quickly than the wood. Not long ago, heat was believed to be a sort of very thin fluid, the pet fluid theory again, far thinner and more delicate than air. This fluid, commonly called caloric, was supposed to flow through the tiny interstices of solids and liquids and among the floating particles of air or gas, passing freely from one body to another. The notion of heat being a fluid, or any kind of substance, is now entirely given up. Like gravitation, like electricity and magnetism, heat is believed to be a force or form of energy. A force has been described as that which changes the form or the place of a body. The said body may be of any imaginable kind or size, from an invisible particle of air, a speck of dust, or an animalcule, to an elephant, a mountain, an ocean, a world, or a sun. Heat certainly does so much. It makes bodies grow bigger. It transforms solids into liquids, and liquids into gases. It alters the very nature of substances, turning one kind into another. It keeps up incessant motion of bodies and substances in the ocean of air. Not that heat alone could do all this, but heat does not work alone. No single force of nature works alone. All the forces toil together, interchangeably, resisting and yet helping one another. The force of heat works with the force of gravitation to bring about the great circulations of air and water, and the forces of magnetism and electricity have a share in the task. When heat passes into a body, it does not always remain there as heat. Sometimes it is transformed into some other form of energy or working power, which again can be transformed to heat. This interchangeableness of the forces of nature is very curious and interesting, though too complex a subject to be more than alluded to here. A cannonball is sent flying through the air by a mighty and sudden expenditure of heat. The heat disappears, being transformed into rapid motion. The ball is then brought to a sudden standstill by a strong stone wall, which it cannot break through. Thereupon the motion vanishes, and heat, so to speak, reappears, great heat being given out at the moment of the ball's concussion with the wall. Another example is found in the steam engine. Heat there goes in as heat, but it comes out in the form of work, the work done by the engine in drawing a heavy train. If the engine is stopped suddenly by a collision, motion ceases, and heat is given forth instead. Even in so small a matter as rubbing two dry sticks together, to gain a few sparks of fire, you have once more an instance of work or motion transformed into heat. One thing that heat is always trying to do is much the same as air and water and electricity are always trying to do. It is perpetually striving after a complete equilibrium. It is ever seeking to distribute itself about, everywhere alike. Heat is incessantly flowing from one object to another, from hotter bodies to colder bodies, that the temperature of all bodies may be the same. Heat passes from hotter to colder bodies, and probably also, in a less degree, from colder to hotter bodies. Each body which has any heat gives forth of that heat, not because some other body needs more, but simply because, being hot, it must radiate or pour out heat all around. Yet undoubtedly the more abundant flow is from the warm to the cold surface, for the general tendency is always towards an equalizing of the temperatures of objects near together. If a body receives more heat than it gives off, it grows hotter. If less, it grows colder. If exactly the same amount, it grows neither hotter nor colder. Heat, therefore, is something which can pass from one object to another. Not only so, but, as with electricity, the quantity which passes is a measurable quantity, and when a certain amount has been given off, less remains behind. Heat flows continually from solids and liquids into the air, also from the air into solids and liquids. On a very cold day, a man's body being much warmer than the atmosphere, a rapid stream of heat pours from his skin into surrounding air particles, leaving his skin the colder. On a very hot day, if he goes out from a cool shelter into a blaze of heat, his skin is the coolest. Then a stream of heat passes from surrounding air particles into his skin, giving a sensation of warmth. Heat entering any substance causes that substance to grow larger by driving the particles further apart. Heat leaving a substance causes that substance to grow smaller by allowing the particles to draw nearer together. This has been gone into earlier. The withdrawal of heat makes a gas shrink into a liquid and a liquid into a solid. There are liquids which actually take up more space in the act of freezing than before, such as water and molten iron. This is only a matter of crystalline arrangement. The actual particles are always closer in a solid than in a liquid, but as the substance crystallizes according to the law of its being, the ice or iron needles lie across and among one another in such a way as to leave empty spaces between, and thus the frozen substance fills a larger space than the liquid did. The broken water pipes of a severe winter are entirely due to this fact. They break, not when the thaw begins, but when the frost first comes. The water in the pipes freezing and crystallizing occupies increased room, and not even strong iron can stand against the sudden and tremendous pressure of the little delicate ice needles. But the breakage is not discovered until the ice melts and pours into the house as water. An experiment has been often tried with small iron bottles, the iron being half an inch thick. Such a bottle is filled with water, is tightly closed, and is placed in cold sufficient to freeze the water. Gradually the water does freeze, and presently more room is required by the newly forming ice needles. Half an inch of solid iron cannot stand against that pressure. A sound of breakage is heard. The thick iron is shivered by the imprisoned forces. This same irresistible power is seen in steam particles. Water commonly boils, passing away as steam at 212 degrees Fahrenheit. On a high mountain, where the weight of the atmosphere above is less than at the sea level, and where consequently there is less air resistance to the flying apart of the water particles, it boils with a smaller amount of heat. Each separate kind of liquid has its own especial boiling temperature, one needing more heat, another less. If a liquid is changed into a gas by boiling, the gas or vapor takes up enormously more room than the liquid did. Heat drives the particles furiously apart. The steam from a kettle of boiling water fills about 1,700 times as much space as the water in the kettle. Repulsion among the steam particles is a mighty power for work, as we well know in the present day, and a mighty power also for danger to life and limb, as seen in boiler explosions. If the steam particles have not room to rush far enough apart in their fierce mutual aversion, they will burst through strong iron, stone, brickwork, anything rather than be compelled to keep closer company. They will not gently and calmly force away like the ice needles, but will burst madly free, dealing damage on all sides. Heat acts much more powerfully upon some substances than upon others. In other words, more heat is needed to raise their temperatures. Suppose you have a pound of lead, a pound of iron, and a pound of water, and you want to make each 4 degrees hotter than it is now. It will take much more than 3 times as much heat to do so with the iron as with the lead, and a great deal more heat still with the water. Or, to put the matter otherwise, suppose a certain quantity of heat is allowed to pass into each of the 3. The lead will then become hotter than the iron, and the iron than the water. Footnote: This difference is spoken of as the specific heat or the capacity of heat of each. End of footnote. Now the fact is, all heat passing into a body or a substance does a definite amount of work there. But the work is not all of one kind. Part consists in eternal changes among the particles of the lead, iron, or water, and this is not apparent to our senses. Part consists in raising the temperature of the lead, iron, or water as a whole, and this is apparent to our senses. With some substances there is more internal work to be done before the temperature can be raised, and so more heat goes to the first, less remains for the second. Or, as it has been expressed, different bodies give heat different degrees of trouble, if I may use the term, in shifting their atoms and putting them in new places. With water, more heat is necessary for the hidden operations than in iron. Therefore, under the same amount of heat, water does not become so warm as iron does. Conversely, when they are growing colder, the water has or gives more trouble in parting with its heat, so it gets cold more slowly. When a body passes from the solid to the liquid, or from the liquid to the gaseous form, the same is seen markedly. If you want to convert a lump of ice at 32 degrees Fahrenheit into water, a large amount of heat must pass into the ice, and that heat will simply vanish. It will all be converted into motion and change among the ice particles. When the ice has become water, the water is not a whit warmer than the ice was. Again, if you have boiling water just ready to pass into steam, far more heat is needed to work the change than was required even to transform the ice into water. Yet, when it is done, the steam will be precisely the same in temperature as the boiling water was. All the heat will have been used up in the internal changes among the water particles. Condensing of steam into water and freezing of water into ice means simply a reversal of the above. Heat then is given out instead of being taken in. Heat is diffused or spread about in 3 different modes. First, it passes or is conducted from one portion to another of a body. If a silver spoon is placed in a cup of hot tea, the warmth spreads upwards through the spoon, being handed on from particle to particle till the end of the handle is hot. Silver is a good conductor of heat. Footnote: Paper is a very bad conductor of heat. Consequently, it makes a good covering for a cold night when blankets are lacking. The poor who sleep out in Trafalgar Square are often seen to use newspapers for coverlets. End of footnote. If a bone spoon is used, the handle will remain cool, since bone is not a good conductor. The heat does literally spread in both cases, but the conduction in bone is so slow that the heat which finds its way along passes off into the air. It is stolen on the road by air particles, and so does not reach the handle end. Secondly, it is conveyed by the movement of a warm body from one place to another. Our British Isles have their moderate temperature through tropical heat being carried northward by the Gulf Stream and given over to us. Thirdly, it is borne by the passage of heat rays from one body to another body at a distance, through something lying between, which does not itself intercept or stop the rays. For instance, the heat rays of the sun pass through the ocean of air, parting with only a small proportion of their heat by the way. Footnote: Any substance which, like air, allows free passage to rays of heat is called diatherminous. Any substance which will not do so is called athermanous. End of footnote. And falling upon the earth. The air alone has a very limited power of stopping the rays, and it is only when they are stopped, only when they are taken captive, that they have a heating effect. Moisture floating in the atmosphere has considerable power to capture and use the heat rays, but dry air has almost none. Heat coming from the sun is called radiant, because it travels in rays, always journeying straight onward. A sun ray may be diffused or spread about by the air, its light being reflected from one particle to another, and it also rebounds from a solid surface, but in itself a ray never bends, never curves. Other objects beside the sun pour forth rays of heat and light. Every heated substance sends out such rays. Whether or no the rays are visible to us depends upon whether our eyes are able to see them. Human eyesight has only a certain range. When a body is too cold for us to feel any warmth at all coming from it, a very delicate thermometer will show that radiation of heat is going on. Rays are given off, which if our skin were sensitive enough we might feel. If our eyes are sensitive enough we might see. When a body is a certain number of degrees warmer, we are aware of the heat rays, not by sight but by sensation. That comes first. Put your hand near a boiling kettle, and you are conscious of the heat radiated forth by the kettle. Those heat rays, though invisible to the eye, might be visible if the retina of the human eye were more sensitive. Every heat ray is also a light ray, but the light is pitched too low for our sight. A certain kind of paper, however, prepared in a particular way, is sensitive to those rays. The photograph of a boiling kettle in the dark, that is to say, in what we count to be darkness, has been taken on such paper by the means of its own light rays, invisible to our eyes. When a body is so much warmer as to become red hot, we see something of its light, though only as a dull glow. When a body becomes white hot, it begins to give forth those brighter rays which we usually describe as shining. It is a curious fact that heat rays, coming from an extremely hot body like the sun, can dart through a substance which would stop or weaken the rays from a body only slightly heated. A sheet of glass has no effect whatever in stopping the sun's bright rays, but it has a marked effect if used as a screen in checking the duller heat rays from the drawing-room fire. The atmosphere, unless when very damp, has an extremely limited power to stop the sun's bright rays. But when those rays have heated the ground, and the ground in its turn radiates heat, the air has a very considerable power to stop the duller rays of so-called dark heat, dark to our eyes only, poured forth by the ground. A conservatory is made on the principle of bright and dark heat rays. The rays coming straight from the sun pass through the glass and heat the interior, but the rays coming from the heated floor and other substances within cannot pass through the glass and are kept imprisoned. Thus the place grows hotter and hotter. We are able to see just so much and so many of the heat rays, which stream from all substances having any degree of warmth, as our eyes are fitted to see. Only that and no more. Our eyes are formed to receive and to use certain rays, not the lowest or the highest in the whole scale of heat and light. Footnote: the belief now universally prevalent is that the rays of heat differ from the rays of light, simply as one color differs from another. As the waves which produce red are longer than those which produce yellow, so the waves which produce this obscure heat are longer than those which produce red. In fact, it may be shown that the longest waves never reach the retina at all. They are completely absorbed by the humours of the eye. I have spoken so far of obscure rays only, but the self-same ray may excite both light and heat. Tyndale's Glaciers of the Alps. End of footnote. Wonderful as it is to think how much we are able to see in the universe, there is something more wonderful still, and that is, how much goes on which we are not able to see. One writer says, "It does not appear that any body can be so cold as to not send forth radiations. Mark this, not any body existing. The reason why all bodies do not appear to shine is that our eyes are sensitive only to particular kinds of rays, and we only see by means of rays of those kinds coming from some very hot body. Had we but eyes to see, what a world of radiance we should find around. All objects that now are dull and plain would shine with unceasing brightness. All that means darkness to us now would then be only varying notes higher or lower in the scale of universal light." End of chapter 29. Recording by Greg Giordano, Newport Richey, Florida.
Chapter 30 of The Ocean of Air, Meteorology for Beginners. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by Melanie Young. The Ocean of Air, Meteorology for Beginners by Agnes GIBERNE. Sound and light. Without heat, the ocean of air would be a frozen mass of solid substance. Without light, the dwellers in that ocean would be plunged into the depths of a perpetual midnight. The rays of heat and light, ever darting down from the great sun, quiver and palpitate through the atmosphere, bringing warmth and brightness to creatures living below. But what are heat rays and light rays? What are rays used in any such sense? This is a difficult subject, hardly to be treated in a few pages, yet not to be entirely passed over. We know comparatively little as yet about the nature of heat, and not more about the nature of light. Many different explanations have been offered at different times to account for the passage of heat and light from sun to earth. None perhaps have been altogether satisfactory. Certainly none can be looked upon as a final settlement of the question. At the present moment, the most widely accepted theory, and that which, so far as it goes, fits in best with what is known of heat and light, is the wave explanation. Waves of many kinds are known to us, notably sound waves in air. Sound, as the term is commonly understood, could not exist without air to carry it. The rate at which sound travels through the air is about 1 mile in 5 seconds. Not nearly so fast as light and electricity travel, yet about 10 times as fast as the most rapid of hurricanes. Everybody knows, or ought to know, that sound takes time to make a journey. The commonest observation shows so much. If we watch rock blasting at a distance, the flash and puff of smoke come first. Then, after a slight pause, the noise of the explosion arrives. In a thunderstorm, the lightning flash is seen first, and unless the storm is close overhead, there is a little break before the peal begins. 5 seconds pause shows that the storm is a mile distant. 10 seconds pause that it is 2 miles distant. During the pause or break, the sound is traveling towards us from the starting point, and not only towards us, but outward in all directions. In fact, it radiates forth, much as heat and light do, only we do not commonly use the word radiation for sound. Any solid substance coming between hinders sound. You may have heard, when listening to church bells as you walked along a road, how at one particular point the sound was suddenly cut off, either lessened or made to cease. A high stone wall had intervened, and the waves of air were turned in another direction. If you had found your way to the right position, you could have heard those same waves of air rebounding from the wall, and you would have called the reflected sound an echo. For sound is conveyed by waves, sometimes described as vibrations or undulations. We must now think for a moment what is meant by a wave. Most people have seen waves of the sea on the seashore. The general impression of a wave is of a body of water pouring onward, curling over, and dashing high on the beach. This is a mistaken notion. Waves on the beach do curl over and do run up the sand or shingle, especially when the tide is coming in. But the true idea of a wave must be taken from the rising and falling of the water a little farther out, say near the end of a pier. Watch a piece of wood floating. A wave comes up, passes under the wood, and flows on, but does not take the wood with it. The wood stays behind. Nay, except on the crest of a breaking wave, you may see the same thing close to the beach. There, too, a piece of wood or seaweed will dance long in one spot, wave after wave giving it a toss, and leaving it where it was. If a wave meant the actual onward movement of water particles, this could not be. The floating object would be carried forward. instead of which the wood and also the water particles among which it lies are at rest. The wave is a vibration traveling through the water particles, not a forward motion of those particles themselves. Such a wave may often be seen traveling over a field of corn. The separate ears of corn do not journey forward. Each in turn bends under the influence of the wave, but each remains where it was. Only the wave changes its place. Sound always springs from motion of one kind or another. Some sudden movement of a body through the air or against another body sets the air particles vibrating and quivering in little waves. These tiny undulations pass on with great speed to particle after particle of the air in all directions. A quick succession of them strike at length on the drum of a man's ear, conveying certain impressions to the brain, which, partly through long practice, the brain understands and translates into certain meanings. But if there were no medium to convey the waves, there could be no sound, however mighty the shock might be of any two meeting bodies. Once again, it should be clearly understood that in these waves there is no onward movement of air itself. The particles of air remain where they were, only they are tossed about a little in the passing wave, as water particles of the ocean are tossed about in passing billows. Imagine what it would mean if things were otherwise, if sound waves meant a literal rush of air particles from the source of sound to the ear. Why, a wind would be set going by every movement of every body on earth, 10 times more violent than the most desperate hurricane of a tropical cyclone. No human beings or human dwellings could withstand it. A good deal was said in the last chapter about rays of light and heat not visible to our eyes. We saw how the world, in even the darkest nighttime of winter, may be actually full of light, radiating from every surface, if only we could see it. The same may be said of sound. There is a scale of sound, as well as a scale of light, consisting of higher and lower notes. In these days of pianoforte practice, the sound scale is a good deal more familiar to people generally than the light scale. We all know from our own sensations how different are the high notes from the low notes of the sound scale. But what we do not know is how much deeper the scale of low notes may descend, or how much higher the scale of high notes may ascend beyond what we are able to hear. Sensation only helps us so far as our hearing extends, and as in sight, so in hearing, our powers are very limited. Some animals on Earth seem to be utterly without voice, without means of vocal communication. What if this only means that their voices are pitched too high or too low for our powers? In a microphone, a microscope for sound, the patter of a fly's footsteps has been heard. If we had keen enough hearing, we might listen to the patter of every insect's footsteps, to the munching of every insect's food, perhaps to the shrill small squeak of every insect's voice. The power of hearing differs greatly in different people. Without reaching actual deafness, there are many degrees of acuteness. The eardrum in some is more sensitive than in others, and the brain is quicker to interpret. Where even a slight degree of deafness begins, the higher and lower notes, especially the former, are at once cut off, and all fainter hissing sounds die out. The inability to detect high notes may be tested at any time by listening to a cricket's chirp. Many people who are not supposed to be deaf and who would probably repudiate the charge with indignation will fail to hear it. If disposed to be over-positive in small matters, they will perhaps deny the existence of the sound, ascribing others' consciousness of the same to fancy. Nothing is easier or more common among minds of a certain caliber than the declaration, "Such a thing cannot be because I do not hear or see it." Deeper and higher notes in the scale of sound mean less rapid and more rapid pulsations of air, larger and smaller waves of air. All kinds of sound reach us at the same rate of speed, but some sounds are formed of bigger undulations than others, so that a smaller number of waves arrive within a certain time. About the deepest note commonly heard by the human ear consists of 16 waves each second. About the highest note usually consists of some 38,000 waves each second. But some people with hearing of rare acuteness can detect yet shriller sounds as high as 42,000 vibrations. The human ear commands altogether a range of no less than 11 octaves. This is by no means to say that other sounds do not exist higher and lower in the scale, formed of yet larger and fewer waves, of yet smaller and more abundant waves. The whole world may be full of sounds which our ears cannot hear, as of light which our eyes cannot see. What we call silence may be no more actual silence than what we call darkness may be actual darkness. Some of the most frequent causes of sound are the sudden striking of one body against another, prolonged friction between two hard bodies, any kind of explosion, and sharp discharges of electricity. All these cause sound undulations through air particles, and in a less degree through the particles of liquid and even of solid substances. It is very difficult to define where noise ends and music begins. The music of certain uncivilized nations, such as the tom-tom rattlings of the Hindus, are mere noise to cultivated ears. Yet probably every continued and steadily recurring sound carries within it at least a possibility of music. The human voice, listened to by one silent person in a full room of talkers, presents a jangle of discordant sounds. But musical possibilities lie enfolded there undoubtedly. A certain degree of speed and of regularity in the vibrations would appear to be needful before any sensation of music can be produced in the listening brain. To return to light and heat in what they are. It is impossible to speak here so decidedly as about sound. The same degree of proof is as yet wanting. We do, however, believe that just as sound consists of waves, so light and heat consist of waves. Only the waves of light are very much smaller and very much more rapid than the waves of sound. Sound waves, which we can hear, vary, as already stated, from about 16 in a second to 38,000 in a second. But light waves are to be counted by millions in a second. A single light wave is believed to be only about 1/500,000,000th of an inch in length. The speed of the two is more easily compared. Sound waves travel through the air at the rate of about 1/5 of a mile in each second. Light waves journey at the rate of 192,000 miles each second. I have spoken of sound waves as waves of air. Now, light waves are not waves of air. Light waves can pass through air, little hindered by it. Light waves can travel in distant space, where no air exists, flashing from star to star, from sun to planets, at the rate just named. Still, if light consists of waves, they must be waves of something. By waves, we mean certain movements or undulations of an actual substance. If space beyond our atmosphere were utterly and absolutely empty, light could not travel in waves. We believe that space is not empty. We believe that everywhere, through the universe, is a certain most fine and delicate something which has been named ether. Infinitely more fine and delicate than air, far too fine and delicate to be tested by any instruments that man has yet made. This ether is supposed to reach from Earth to the sun, from the sun to all planets and stars. It fills all space, it pervades the atmosphere, it enters into the make of all liquids and solids. Through this wondrously fine and invisible ether, the waves of light are sent, vibrating, thrilling, oscillating, quivering, down to earth from the blazing sun, traveling with such marvelous speed that imagination cannot picture it. Whether light waves as such do in very truth exist cannot yet be positively asserted. The wave explanation may in the future have to give place to some other theory. We do know, however, that light travels in some such mode, through some such medium. While we cannot be certain that light actually comes in waves, like sound, we know the speed of light, for that has been measured. And we know that light consists of a certain definite number of somethings each second. Whether we call them waves or no, for those somethings have been counted. Red is at the lower end of the light scale, corresponding with the deepest bass note known to our ears. Violet is at the higher end of the light scale, corresponding with the shrillest treble note known to our ears. The exact pitch of any one musical note, or indeed of any sound, depends entirely on how many waves of sound pass into the ear in 1 second. For a bass note, the waves are larger and fewer. For a treble note, they are smaller and more numerous. It is the same with light. The exact color of any object depends upon how many waves of ether pass into the eye in 1 second. For red, the waves are larger and fewer. For violet, they are smaller and more numerous. About 39,000 tiny light waves in 1 inch mean, as they reach the eye, the sensation of red. About 57,000 waves in 1 inch mean the sensation of violet. Between these two range all other tints visible to human sight. Beyond them, higher and lower, our seeing powers fail. Of course, sight, like hearing, varies markedly in different people, some having a far wider range of vision than others, but these are generally accepted as the outside limits. It should be noted that I am speaking now of the size of light waves in respect to space, not their speed in respect to time. There are so many vibrations in the second belonging to red and so many belonging to violet, but these are enormously high figures. People in general do not much care to hear about millions and billions. Those rapid light waves coming from the sun, which give to our eyes the sense of brightness, are not by any means the whole of the keyboard. It has a far wider range. Beyond the red, low down, are other sun rays, deeper notes known to us only as heat rays. We can feel them as heat, but we cannot see them as light because they are formed of waves too big to affect our eyes. Whether some animals may be able to see them is another question. Again, beyond the violet, high up, are yet other sun rays, known to us only as chemical rays. These are formed of waves too minute and rapid for our powers of vision, nor are we conscious of their small amount of heat. But the chemist is well acquainted with these rays, and the photographer knows how to use them on prepared sensitive paper which, if paper can be said to see, does see, or at least is affected by, them. When the sun takes a man's likeness, he does it by means of these invisible chemical rays. A ray of white light is a bundle of many colors. When, by allowing it to pass through a prism, the ray is broken up, the various tints of which it is combined are seen. Instead of a single white ray, a series of colored rays are seen: violet, indigo, blue, green, yellow, orange, and red, extending from the top to the bottom of our sight scale. The ear has command of 11 octaves of sound, but the eye has command of only about 1 octave of color. Not long ago, it was the fashion to talk about the 3 primary colors, red, yellow, and blue. After a while, these were altered into the 3 primary colors, orange, green, and violet. Now, all the chief colors of the spectrum, as given above, are counted to be simple or elementary colors, from which all other colors are made. Black and white are not colors. Pure black means the absence of any tint at all, while white is the union of all the rest. If you look at a mass of soap bubbles from near at hand, you will see all the different hues of the light scale on the thin films of soap and water. But if you go to a distance, the colors will unite before reaching your eyes, and the bubbles will appear white. A ray of light passing through a prism is broken up and dispersed, each color ray which helps to form it being bent and thrown upon the wall or ceiling at a different angle. This is said to be done through refraction. If light rays could not be refracted and dispersed, we should lose all our sunrise and sunset tints. The crimson of the clouds, the opal of the skies, the golden glows would be nowhere. A light ray, until dispersed, is always white. Red and yellow tintings in the heavens mean always the breaking up of white rays, that some of the hidden brighter colors which unite to form white light may become visible. This scattering of light, which produces not only the brilliant hues of morning and evening, but also the blue of the air and the sky, is now believed to be largely the work of fine floating dust in the atmosphere, assisted by minute floating particles of water vapor. Dispersion of light is also markedly seen with rainbows. For a rainbow to appear, there must be sunshine as well as rain, and the observer must stand with his back to the sun, his face to the bow. Any number of observers may be present, and any number of rainbows. Each individual sees a bow, and all speak of the bow, but no two among them see the same bow, because no two can stand in exactly the same spot at one time. A rainbow is caused by the reflection and refraction of the light waves on the falling raindrops. Each raindrop acts as a prism, breaking up and dispersing the rays of white light so that a succession of tinted rays are seen from violet to red. Each observer's eyes must be in the direct line between the sun and those falling drops which, acting in quick succession, serve for his prism. Sometimes the bow is single, sometimes double. Sometimes the colors are more clear, sometimes less clear. The conditions are the same, however, for all observers gathered in one place, and the effect upon their vision is the same, so that it is as if all saw one bow. What a dull, colorless ocean of air our dwelling place would be, if no light rays could ever be broken up, refracted, or reflected, if no crimson and purple and golden hues lit up our evening skies, or shone as rainbows through the raindrops to relieve the dead level of perpetual whiteness. End of Chapter 30. Recording by Melanie Young.
Chapter 31 of The Ocean of Air, Meteorology for Beginners. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by Elizabeth Miles. The Ocean of Air, Meteorology for Beginners by Agnes GIBERNE. Atoms and Molecules. Chapter 31, Atoms and Molecules. Particles of air, particles of water, particles of solid substances have been often spoken of in past chapters. There is no such thing to be found on Earth, or, for aught we know, in the universe, as a substance which is not formed of particles or little parts joined together. There are no substances so uniform and solid in mass that they cannot by any possibility be divided. Granite rock is hard, but granite can be melted or broken, can be crushed, and even ground to powder. Diamond is hardest of them all, but diamond can be cut and altered in shape, particles of diamond being removed from the main body. Suppose you take a lump of soft sandstone rock and break it in two, then break the half, and again the quarter, dividing and subdividing till you have a piece too small to be divided further. Still, that tiny lump can be pounded and only fine yellow sand remains. Each grain of sand lying there is a particle, one of the many particles which helped to make the lump of rock. A grain of sand is small, but put that grain under a microscope and behold, it grows into a big jagged rock consisting of any number of minute particles. So we are by no means at the end of things yet with the grain of sand. The only question as to further subdivision is as to the fitness of the tools at our command for such delicate work. Each separate body upon Earth, whether a solid, a liquid, or gaseous body, is believed to be made up of countless multitudes of most minute particles of matter, which are called molecules. Each molecule is made up of other still smaller particles of matter, which are called atoms. A single molecule of any substance is exceedingly small, smaller than the tiniest speck you can possibly imagine. Yet a molecule is made up of atoms. Therefore, a molecule must be larger than an atom. Suppose you have a drop of water. How many molecules would you think there are in the drop? I cannot answer that question for you. The drop, however, may be divided. You may have a smaller and smaller drop till you get down to one of those minute specimens which float in the air during a fog. But it is still enormously far off from being only a single molecule. Even such a drop under a powerful microscope will be quite a little pond, and if taken from a real stagnant pond, might contain living creatures. The very tiniest and lowest of living creatures is believed to be made of, at the least, somewhere about 1,000,000 molecules. You see what an immense number of molecules must be in one ordinary water drop. Now, suppose that by dividing the drop, or by evaporating most of it, we could obtain the most infinitesimally minute water speck, so minute to be not only invisible, but utterly incapable of any further lessening or dividing. Then you would have a molecule of water. A water molecule is the smallest speck of water which can exist, being still water. One may divide or subdivide or lessen in size any object to a great extent, but one cannot go on at that work forever. While a water molecule is the smallest imaginable speck of water and cannot be further diminished in size as water, it may be divided into something else. It may be separated into the atoms of which the water molecule is made. Heat alone will not do this. Heat can transform solid water into liquid water and liquid water into gaseous water. Yet the molecules of the ice, the water, the vapor, are all alike in kind, are all the same in make, the same in weight, the same in character. The only difference is they are differently arranged and placed nearer or farther apart. You will remember that water is made out of two gases, the good, useful oxygen, so needful for combustion, the light hydrogen, so important for flame. Each water molecule, each ice molecule, each vapor or steam molecule is alike formed out of one oxygen atom and two hydrogen atoms closely united. I do not say that water is made of these two gases, but out of them. The two gases disappear and the water appears instead. The simple oxygen molecules made of oxygen atoms and the simple hydrogen molecules made of hydrogen atoms are split up, broken to pieces, and new compound molecules are formed. Each atom of oxygen seizes upon and is seized by two atoms of hydrogen in a firm embrace. As this triple alliance takes place, and in the very act, the gas atoms and molecules vanish, and a new water molecule has come into existence. Heat is the power which commonly brings about new alliances in atoms. But if you want to break up the water molecules again, you must do something more than apply heat. A stream of electricity poured through the water will break up each water molecule into its original gas atoms. Much was said earlier about the elements or simple substances, those which cannot be broken up into other substances. An atom must always be the atom of a simple substance, never of a compound substance. You may have an atom of oxygen or of carbon, of hydrogen or of gold, of silver or of iron. You cannot have an atom of water or of glass, because the smallest possible speck of water or glass is always formed of two or more other substances. It is a molecule, not an atom. A rough calculation has been made that about 50 millions of hydrogen molecules placed in a row might perhaps reach an inch in length. Footnote: it has also been reckoned that about 2 millions of hydrogen molecules in a row might extend to a millimeter in length, and that about 200 million of them might weigh a milligram. There is, however, no pretense at exactitude in these statements. An atom of hydrogen, as the smallest and lightest mass of matter known to science, is said to weigh 1 microkrith, thereby forming a standard of weight among atoms and molecules of different substances, the relative weights of which are well known. An atom of oxygen weighs about 16 microkriths, or 16 times as much as an atom of hydrogen. An atom of iron weighs about 56 microkriths. An atom of gold weighs about 197 microkriths. End of footnote. An atom is that which can never be divided, can never be made smaller, can never be changed in nature or form by any of the known forces of nature. There is a great deal that is very singular and mysterious about the character of atoms and their union into molecules. The atoms of certain substances have what is called an affinity, an apparent liking for the atoms of certain other substances, and this liking is always mutual. Where the affinity exists, the atoms of different substances will unite chemically under heat or some other force to form fresh substances. Where the affinity does not exist, no power on earth will cause them to unite. The atoms will always unite in a particular manner, after certain definite modes and proportions. Even where this curious affinity is found between them, they will not consent to be jumbled up in any sort of mass. Suppose you want to turn a quantity of hydrogen and oxygen into water. You may bring together as much of the two gases as you please under the right conditions, but you will never get the atoms to unite in any other manner than exactly 1 of oxygen to 2 of hydrogen. The same peculiarity runs through all the atoms and all the molecules of all different substances. Each particular kind of atoms will combine with just so many, never more or less, of certain other substances, and with none but those. There seems good reason to believe that each atom of matter is in itself an infinitesimal magnet with its 2 or more poles. These poles, attracting and repelling, will unite or refuse to unite with the poles of certain other atoms. The question of affinity among atoms may be, partly, a question of magnetic poles. So, if things are as we suppose, the Earth as a whole is one huge magnet, and that magnet is made up of countless millions of infinitesimal atom magnets. All molecules of any one substance are believed to be generally alike in size, in weight, and perhaps in shape. A gold molecule is like every other molecule of gold, but unlike molecules of iron or glass. A water molecule is like every other water molecule, but unlike molecules of mercury or silver. The molecules of each separate substance, yet more the atoms of which they are formed, are different altogether, in nature and in modes of action, from the molecules and atoms of any other substance. These differences seem to be sharply drawn. No intermediate connecting links have yet been found. Each kind of atom stands alone, clearly defined, permanent in kind, unchanged through countless ages. Each atom, each molecule has been stamped with certain characteristics, made subject to certain rules or laws. The inherent characteristics remain always the same. The rules or laws are followed with the absolute submission of lifeless, mindless matter. The molecules of a solid substance are held in place by attraction, the attraction of cohesion or of sticking together, spoken of in an earlier chapter, and they certainly do seem to stick together. Yet in reality they are far apart, far, that is, in comparison with their size. Every particle in a lump of iron attracts every other particle, the power of cohesion binding the iron dust into a hard mass. But every particle in the iron also keeps aloof from all the other particles. Probably no substance on earth is so solid that it might not become more solid under great pressure. In other words, the particles are never so near that they cannot be forced nearer. This is a fact not so difficult to realize with reference to a gas or vapor, with reference to the light elastic air in which we live, but much harder to grasp with reference to a solid mass of iron or stone or gold. End of chapter 31.
Chapter 32 of The Ocean of Air, Meteorology for Beginners. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by John Brandon. The Ocean of Air, Meteorology for Beginners by Agnes GIBERNE. Chapter 32, A Busy Whirl. We have seen how in the whole ocean of air there is no fixity, no stagnation, except indeed where that stagnation reigns, which means death to the individual. In the world of matter, all is change and motion. And in the restless enfolding atmosphere of Earth, this is especially seen. Air, gas, water flow to and fro in ceaseless circulations. But to turn for a moment from our main subject, the air, in a mass of stone or iron, we should certainly expect to find repose. Yet nothing of the kind is there, or at least it is the repose only of well-ordered motion. Each separate molecule in a solid substance is believed to be a tiny system of quivering atoms. Each atom has its own minute perpetual motion, its own pathway of incessant gyrations, as surely the result of conflicting forces as the whirl of planets around the sun. And as atoms tremble about atoms in their tiny spheres, so molecules stir among molecules. The molecules of a solid substance have no doubt very limited movements, but in a liquid they are free to wander throughout the whole extent. The speed with which they do wander may be easily seen. If a small quantity of red liquid is put into a basin of clear water, the pink tint carried by traveling molecules will at once spread to all parts of the water. The movements of air and gas molecules are yet more untrammeled. If the gas is free, they fly widely apart with the utmost haste. If the gas is confined within a vessel, the molecules keep up a constant cannonade of the vessel walls, striking and rebounding in the effort to escape. The force of such a cannonade, in the case of heated water, gas, or steam, is well known in these days of steam power. A gas, in fact, consists of molecules in motion. When near together, acting one upon another; when far apart, pursuing their own paths independently, but always on the move. It has been circulated that when hydrogen gas is at the freezing point, its molecules rush about at the rate of over 2,000 yards each second. As the gas is heated, this speed rapidly increases. Molecules of air, that air which you and I breathe in a common sitting room, are incessantly careening to and fro with great speed. As they come into perpetual collision one with another, no single molecule advances far in any direction without being turned back. These molecule movements must not be confused with the general movement of air, which we call wind. The two are as distinct as are the motions of iron molecules within an iron ball, and the motion of that ball as a whole when it is sent flying from the mouth of a cannon. By a collision of molecules, it need not be understood that the molecules actually touch. Probably no one particle of air, or of any substance, ever really touches another. It is enough for collision purposes if two rush so close together that the proximity is unendurable to their repellent natures, or at least to the repellent side of their natures, since, like most human beings, they have a repellent as well as an attractive side. Each then rebounds from the other, to come immediately into collision with the next molecule. The probable and possible number of such collisions has been roughly calculated, and it sounds a little startling. For a molecule of hydrogen gas, not unusually heated, the medium length of peaceable travel among its neighbors is held to be about 4/1,000,000th of an inch, while the collisions themselves number some 18,000 millions in a second. The strong smell of ammonia is well known. When we speak of the scent of any substance, we really refer to countless tiny particles of it, which detach themselves and float away in the air, thus reaching the sensitive nerves of our noses. Now, just as a little red liquid put into clear water will spread fast through the water, so a little scent in a room will spread fast through the room, yet not so fast as one might expect. Ammonia particles travel at a rapid rate. When not hindered, they rush about at a speed of some 600 feet each second, so it would not take them long to reach the farthest corner of the biggest room ever built. Only they always are hindered. The air hinders them. Each ammonia particle has to fight a fierce battle for every inch of advance, striking against and rebounding from the particles of air which oppose its passage. There really is plenty of room for the ammonia molecules among the air molecules, if only they would move quietly. But the rhythmic dance of these minute specks of matter seems to be highly excited, not to say combative, in kind. We have seen how great a power heat is in the wide ocean of air. Heat tells upon the motions of all particles of matter, so much so that it is sometimes said heat is motion. The more hot any substance grows, the more rapidly its particles vibrate. Suppose heat to be passing into a lump of ice, steadily raising its temperature. The ice molecules, already stirring and trembling, stir and tremble now more vehemently. Also, they begin to move farther apart, leaving wider spaces between one and another. The ice grows larger. As more heat enters, the molecules vibrate with greater rapidity, becoming still further separated. The force of cohesion is thus weakened through the greater distances dividing the particles. Presently they flow in and out among each other, and the solid ice has become liquid water. If yet more heat enters, the same course of events is repeated. The whirl of liquid particles grows faster and faster. The molecules separate more and more widely. The attraction between them is lessened. The water grows larger and lighter. Finally, the molecules break loose altogether from any semblance of cohesion, repulsion winning the day. They rush as far as possible apart, and the liquid has become a gas. But why should heat cause wider separation among the particles? Is it a matter of repulsion strictly? In the solar system, the sun occupies the center, and the planets revolve around, each in its own pathway at a certain distance. The sun mightily attracts the planets, drawing them towards himself. Yet they never fall in upon the sun, for another force is at work, balancing the attraction, keeping each in its own place. This force is not repulsion. The sun does not repel the planets. He only attracts. And the counterbalancing force is the swing or impetus of each planet's rapid motion. If the planets all began to go faster than at present, they would all move to positions farther off from the sun, and so the whole solar system would extend in size and would take up more space. Now think of a lump of ice as a little system of moving particles, not absolutely unlike the solar system of moving worlds. When additional heat enters into the ice, the particles already in ceaseless motion begin to move more rapidly. And then? Well, and then? Why, naturally, the swing or impetus of each particle's increased speed carries it a little farther away from other particles. The dividing spaces between grow wider. The ice as a whole expands, taking up more room. Heat appears to have worked this, not indeed by increasing the repulsion among the particles of ice, but by causing them to move, to swing and circulate, so much more vehemently that each particle is carried to a greater distance from its neighbors, till the whole melts into a liquid. And as comets sometimes break loose from the solar system through the violence of their own rush, so it is often with the molecules of a liquid. The vibration is so increased by added heat that all mutual attraction is at last overcome, and the particles fly widely apart as a gas. But for this possibility, there could be no ocean of air. The analogy between the two, between the movements of whirls and the movements of molecules, is at least suggestive, if indeed the latter exist. but we still have to make that proviso. The story of molecules and atoms is a well-founded theory, a most probable explanation, which meets the difficulties of the case better than any yet proposed. Whether it will stand firm in the future remains to be seen. These questions are now closely searched into, and rightly so. One cannot look too earnestly into the world of nature, which is the handiwork of our Father in heaven, the outward expression of his thoughts. We have tried to find the reasons and causes for many things seen in daily life. Rightly so again. All results spring from causes, and there are reasons for everything on earth. Such seeking is not skeptical. With God nothing is impossible. This we know, and it stands to reason. He who creates can create as he will. He can act through the forces which he has created as he will also. But we know that our God is a God of order, a God of law, as well as a God of love. Plainly, it is his will that cause and effect should be always united, always balanced, albeit not always understood by us. I have spoken earlier of many shut doors, where outsteps are stayed, at least for the present, for his ways are past finding out, so that no more shall remain to be found out, not past looking into and examining, not past finding ever fresh wonders, ever fresh delights, ever fresh opening of hitherto fast shut doors, which shall land us on the threshold of yet other doors, with locks that need patient picking. As many intervening causes as we care to picture may lie between any one effect in nature and the supreme first cause. Turn, however, where we may, search where we choose, we reach always at the last a wall of mystery. Beyond that wall, it may be nearer, it may be farther, yet never very distant is God himself, upholding all things by the word of his power. End of chapter 32. Recording by John Brandon.
Chapter 33 of The Ocean of Air, Meteorology for Beginners. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. The Ocean of Air, Meteorology for Beginners by Agnes GIBERNE. Chapter 33 Dust of the Air. The ocean of air, as we have already seen, is a mighty carrier of fine dust. What an amount of dust there is in the world, and how little we commonly consider where it all comes from. Clouds of dust, swept along by a March blast, are suggestive of colds and coughs, no less than of a good harvest worth a king's ransom. March dust is coarse, rough, gritty, a foe to eyes and throats. Other kinds may be finer, yet not less injurious. We hear of such dust in manufactories, perilous scrapings and filings which float about, and are breathed into the lungs, to tell upon frail human organs shortening life. A deadlier dust, this, than the wickedest road grit of an English march. The busy air ocean bears all kinds to and fro. Dust is plentiful enough, not to say more than enough, at all times and everywhere, a companion which we labor to keep out of sight in our homes, but which never can be exterminated. Each grain or speck of dust, however small, is a mass of atoms, and atoms cannot be put out of existence by any force at our command. After all, dust may not really be more than enough in quantity, if, as some think, it is absolutely needed for the formation of every mist, every cloud, as well as every fog. We could not do without clouds. Still, there is an aggravating persistency in dust. Strive as we may, it is never got rid of. Open the window to let it go, and the very air which carries it off brings in a fresh supply. Rub a mahogany surface bright as a mirror, and lo, before you can turn away, tiny gray specks are settling down again. In fact, the most we can do is to act the part of a London policeman with perpetual "move on" to the little vagrants. They do move on, no doubt about that. Dust is never long at rest. Perpetual circulation of dust is as true as perpetual circulation of air, though less important to us. There are many kinds of dust in the world, some, such as gold dust, having a market value. But in treating of common dust, gold may be put out of our calculations. Though doubtless a minute speck of it does wander here and there through the depths of the air ocean. We do not generally realize how full our rooms are of dust. Unless the atmosphere is unusually laden, our senses do not make known the fact. Dust specks are forever traveling here and there, up and down, north and south, east and west, uncontrolled as the winds themselves, in a continual restlessness. They are always settling down somewhere, yet the air is always crowded with them. Most of this goes on unnoticed by us, but let a room be left a few days undusted, and results are patent enough. Or let a ray of bright sunlight stream in, and a whole world of dancing many-hued motes is revealed. Where do all these motes come from? From everywhere, from anything, from all imaginable surfaces. As varied as are Earth's substances, so varied are the kinds of dust floating in the air ocean. No substance probably exists which does not under common conditions part with minute portions of its surface, those portions passing away as fine dust into the air. More or less everything crumbles, everything wastes. The wear and tear of friction in daily use make dust. The rubbing of one body against another makes dust. The progress of growth and decay makes dust. The effects of frost, rain, and wind are to make more dust. The mere action of damp air, in even a reposeful mood, brings about the crumbling of hard surfaces, and so makes dust. With certain substances hard friction is needed to wear the surface, but in a greater number there is a constant giving off of fine particles to be added to the array of dust. Above and beyond all these sources, great quantities of meteorite dust are ever coming into our atmosphere from distant space. These and other kinds float into the ocean of air, the heavier motes dropping the soonest, the lighter borne to and fro indefinitely, even at vast heights above the earth. It has been already explained in earlier chapters how the formation of fogs and clouds, the blue of the air, the fair colors of sunset, the brilliant hues of the aurora borealis, are all believed to be more or less due to fine floating dust in the atmosphere. If one could analyze the dust specks collected in a single room, curious results would be obtained. Among 100 motes, perhaps a few might own to the same source. This from a log of wood, that from a mass of metal, this from the skin of a man, that from the fur of a beast, this from a woolen dress, that from a shabby shoe, this from the stem of a tree, that from the petal of a dying daisy, this from a pile of volcanic debris, that from a chalk cliff, this from a coal in the fireplace, that from the frond of a fern, this from a fallen meteorite, that from the dried silt of a riverbed, this from the wing of a butterfly, that from the pollen gatherings of a busy bee, and so on ad infinitum. Light substances are often carried to immense distances by moving currents of air, especially in the upper regions of the atmosphere. Just as a quickly flowing river can keep earth and sand long afloat, so rapidly moving streams of air can keep fine dust aloft, for an almost indefinite length of time. Great quantities of salt are carried by winds from the ocean over the land. When gentle evaporation takes place on a still day, the vapor passes upwards, leaving its salt behind. But when winds stir the surface of the sea, lifting waves and catching away the salt spray, they bear salt and spray together, sometimes for many miles inland. Towards the end of April 1882, a very severe storm reached our shores from America, happily not without previous warning, so that the damage done to shipping was less than it might have been. The winds blew furiously, amounting even to a hurricane in force. Some gusts were known at Kew to travel at the rate of 70 or 80 miles an hour. A remarkable feature of this storm was its effect upon the fruit crops. Apple blossoms in multitudes were swept away, and those that remained had grown black, as if with blight, while the young leaves might from their look have been scorched by a withering flame. In gardens and in woods the same was seen. The foliage of plants, shrubs, trees, more especially on the windward side, being shriveled and blackened, as if with sudden decay. This was not the result of sharp frost, for though cold it was not frosty. What could have caused so unusual a result perplexed many. Somebody offered a suggestion that the salt-laden condition of the winds might form a clue to the mystery, and in the next report from the Kew Observatory this idea received strong support. In proof of its probable truth, 3 interesting facts were stated. At a certain place in Dumfriesshire, about 50 miles from the North Sea, during strong east winds, the presence of salt spray had been detected on the leaves of evergreens. A calculation had been made, as the result of careful examination, that at Penicuik, near Edinburgh, 10 miles away from the sea, every acre of land receives yearly, through its regular rainfall, no less than 640 pounds weight of salt. In ocean storms, salt flung by the winds with water into the air often renders the atmosphere so dark that sailors can see no way ahead. By a strong gale, such salt spray might well be carried 40 or 50 miles. These facts help to explain the carrying of salt from place to place. But in truth, the air is at all times more or less full of salt, floating as fine powder among the floating motes of the air ocean. If salt is thus borne to and fro, much more will fine dust by the sport of breezes and winds. Dust is frequently carried away from deserts and volcanoes for hundreds or even thousands of miles before being dropped to earth. When it does descend, it may come down gradually, winning no particular attention, or it may fall as a sudden dust shower. Falls of dust have often taken place at Malta, at Genoa, and in the south of France, and the dust was commonly supposed to be African in its origin. On certain occasions, however, when carefully examined, it was found to be quite different from the dazzling white sand of Sahara, being instead of a reddish-yellow color, and both in itself and in the microscopic creatures it contained, it was known to be a kind peculiar to South America. About the middle of the present century a tremendous storm visited Lyons and Grenoble, bringing with it the unusual phenomenon of red rain. Blood rain or blood-red rain people called it, though the tint was not strictly so red as blood. Some of the rain was carefully secured and put under the microscope. The coloring was then found to arise from a large amount of the reddish-yellow dust mentioned above being mixed with the raindrops and lending to them of its own reddish hue. Footnote: the red of the dust was found to be due to iron oxide. End of footnote. Many falls of so-called blood rain had been known earlier, and nervous people were greatly terrified by them, but for a long while the simple solution of the puzzle was not discovered. Red snow, as well as red rain is sometimes seen, the coloring of the snow being due to a very minute vegetable growth. Here again, the busy winds must have been at work, carrying germs. The cause is not necessarily always the same in either case. One famous historical instance of red rain was at The Hague in 1670. People generally regarded the visitation as an omen of war and disaster, but a physician living thereabouts looked into the liquid with his microscope. Although microscopes then were not what microscopes are now, he made out easily that the water in itself was unchanged, but that it was filled with countless myriads of minute lively red insects, a kind of tiny water flea. The only possible explanation of their sudden descent from the clouds was that the winds must have called them up elsewhere, brought them from a distance, and poured them down with the rain. Early in the present century, a remarkable fall of inky rain was known at Montreal in Canada. Here, however, a solution of the mystery lay ready to hand. Microscopes speedily showed that the blackness of the raindrops was due to soot. An immense forest fire had taken place far away, south of the Ohio River, and prevailing south winds had borne masses of soot from the great conflagration to the skies of Canada, thence to be showered down, mixed with water, as black rain. Few who saw them will forget the extraordinary sunsets of November 1883. Red and pink, orange and yellow, green and purple glows were contrasted often with streaks of ebony cloud. One evening the western sky would be all aglow with orange, another evening the whole was bathed in crimson. The moon was sometimes a clear steel blue, sometimes a distinct green. Even in smoky London magnificent sky effects were visible, and wonderful reports came from around the world, from the Mediterranean and the Pacific, from India and Australia, from Canada and the United States. Those who rose at an hour to watch for sunrise were rewarded by like visions of beauty. No common conditions in the ocean of air could cause this display, lasting through many weeks. A mighty eruption of Mount Krakatoa in Java had taken place that summer, such an eruption as our earth seldom knows. For those near the spot it was a terrible experience. Black darkness reigned for scores of miles around. There were fierce lightnings and balls of fire, and crackling noises in the atmosphere, mingled with continual crashes as from heavy artillery. The sounds reached, indeed, to an utterly unprecedented distance. Over 90 miles off, the noise was simply deafening, while it could be distinctly heard at Rodriguez, nearly 3,000 miles away. Yet, strange to say, the explosions which literally blew to pieces 2/3 of the mountain, though audible over 1/14 of the entire surface of earth, were not so much noticed in the neighborhood of the volcano. No doubt the thick clouds of dust filling the air deadened their roar, as a dense fog or thickly falling snow deadens sound. The vast mass of materials bulged upward in a black cloud from the rent and shattered mountain was estimated to be about 17 miles in height. Pumice, dust, and ashes were rained lavishly upon land and ocean for hundreds of miles around, all heavier pieces and coarser dust falling comparatively near. But enormous masses of light friable glassy dust, carried to lofty levels in the atmosphere, were borne away by winds to far distances. Consequent on the great explosion, a wave of water 50 feet high was sent careering through the strait into the Southern Ocean, while an air wave of unexampled grandeur went circling round the world. On the very same day, a thin white mantle was drawn over the blue sky for 1,000 miles to the westward, the sun shining dimly through, like a dull reddish lamp. Then followed the remarkable appearances already mentioned: green and blue and coppery suns, green and blue moons, skies of gorgeous radiance, clouds of burnished gold, copper, brass, silver, such as Turner in his wildest dreams never saw. We have already seen how the common blue of the air, the ordinary tints of sunrise and sunset, are believed to be largely due to fine dust floating in the atmosphere, both dust of solid materials and liquid water dust. Here, in the abundant pumice dust of Krakatoa, was an intensified form of the same cause, intensified results in the way of coloring being therefore produced. The masses of dust traveled fast. Mounting to a great height above trades and anti-trades, they were caught in the embrace of a full fair easterly gale, an unresting hurricane, the very existence of which had not before been conjectured, and were hurried with extraordinary swiftness round the earth. The whole tour of the equator was accomplished, it is believed, by these clouds of volcanic dust in less than a fortnight, and still they circled round and round for many weeks, even for months, giving to mankind the grand sky displays of that year. Gradually the dust became dissipated in all directions, but as for dropping to earth, that is a slower matter. No reason is known why dust, once lifted 50 or 60 miles above earth's surface, may not remain there for years. In Holland and in Spain, dust material brought down by snow and rain at the time of these radiant sunsets was examined. In both cases it was said to contain volcanic dust, apparently agreeing in kind with the ashes thrown from the crater of Krakatoa. Dust storms in India are of common occurrence. Sometimes they advance as a broad wall of dust, composed of a number of separate columns, each column being a small whirling cyclone of wind, thickly laden with dust. Such a column may be seen only 5 or 6 feet in diameter and 50 or 60 feet high. Electricity has no doubt a hand in these storms. A regiment on march in the Punjab was once caught in a severe dust storm followed by rain and lightning. As the rain came down, the tips of the men's bayonets and the peaks of the caps worn by the officers were seen shining with a curious electrical light. Enormous quantities of dust are swept up from earth by the upward whirling motion of these small cyclones, and are often borne to an extraordinary height. It has been doubted whether dust showers alone would account for nearly so much as is carried aloft. Dust storms are known to Australians as well as to inhabitants of India, and everybody naturally connects them with deserts. With respect to Egypt we read, "In the early spring the Khamseen does indeed afford a very unpleasant change to comment upon. It is a hot dry wind laden with fine particles of dust, which penetrate everywhere, fill one's eyes and ears, irritate the skin, and produce a sense of extreme discomfort. Everything is seen through a lurid haze. The sands of the desert are whirled by it into rotating columns, which march to and fro till they suddenly break up and disappear. On the river this is merely a cause of annoyance, but in the desert it becomes a serious danger. Caravans are said to have perished and been buried beneath the drifting sands." Footnote: From The Land of the Pharaohs. End footnote. The Khamseen of Egypt is identical with the Simoon of Arabia, and the burning Sirocco of Italy is believed to be the same, only tempered by its passage across the water. The following sketch of a so-called Sirocco, from the pen of a French army surgeon accompanying French troops in North Africa, sounds like the genuine desert blast. It was towards the end of July, 1846. Several soldiers had succumbed to the heat. The Sirocco assailed our little column. Under the influence of this dry, heavy, and enervating air, the breathing became difficult, the lips and the nostrils cracked by the burning dust driven up by the wind, were both dry and painful, and the throat, as it were, became contracted. The face was burnt by gusts of heat, sometimes followed by tremor and a fainting away, which resembled syncope. The perspiration ran off in streams, and the water which was eagerly swallowed did not quench the thirst, but increased the stomachic pains and the difficulty of breathing. To walk would have been impossible. We felt half suffocated under cover of the tents, and in the open air the burning breeze caused a choking sensation. But for the water, our column must have perished. Footnote: From The Atmosphere by C. Flammarion. The simoon of the desert is worst and most frequent at the time of the equinox. Commonly it is first seen as a distant black spot which rapidly draws nearer and grows bigger. Then a rush of burning sand-laden air arrives, from which birds and beasts flee in abject terror. A camel turns his back to the blast, and if possible finds a bush to shelter his face. Simoons vary greatly in degree, some travelers having met with far slighter ones than others. At the best, the scorching air and drifting sand cause much bodily discomfort, but at the worst they mean extreme peril to life. Early in the present century, an entire caravan, consisting of 2,000 men and 1,800 camels, were all overwhelmed and suffocated by simoon. It is believed that the 50,000 soldiers sent by Cambyses against the temple of Jupiter Ammon perished in the same way. One can well imagine the difficulty of breathing such burning air, thickly filled with fine particles of hot sand. It is in fact the same danger as that encountered by the American caught in a blizzard, the danger of being stifled. Human lungs are not made for densely thickened air, whether the thickening arise from cold snow dust or from scorching sand. End of chapter 33. Chapter 34 of the Ocean of Air, Meteorology for Beginners. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. The Ocean of Air, Meteorology for Beginners by Agnes GIBERNE. Chapter 34 Living Dust of the Air. Among the dust specks which fill the air are other minute things, not strictly dust, smaller far than the motes which we can see, invisible except under a microscope, and altogether different from mere dust, because they have in them the gift of life. These make their home in the atmosphere, floating everywhere, mingling with the air particles in countless multitudes. It has been stated that with every single breath a man breathes he may draw scores or even hundreds of them into his lungs, yet they are so minute that they do not put him to inconvenience. Many of these living germs of the air, infinitesimal rod-shaped forms of vegetable life, are less than the 100,000th of an inch in length. They are, however, exceedingly active and frightfully prolific. One of the bacteria has been said to increase in the course of 24 hours to over 16 millions. Some kinds grow by rapid dividing and subdividing, each rod-like thing becoming two, which two divide each into other two, and so on. Others increase by means of spores. As spores they can endure wide variations of cold and heat. They may even become perfectly dry like dust, seemingly dead, yet afterward they will revive. This constitutes a danger to mankind, for air abounds in such germs and spores, and water is perhaps fuller still. They are germs of putrefaction often, germs of disease sometimes. If any vegetable or animal food is left within touch of air or water, wandering germs will speedily seize upon it, feed upon it, turn it bad, as we say. Food, to be saved for any length of time from these destroying multitudes, must be shut off from the touch of water or air, hermetically sealed in a dry vacuum. But men cannot be so guarded from wandering germs of disease. It is extraordinary how long such germs, or at least the spores of them, will keep their vitality. In the olden days of plague visitation, clothes from a plague-stricken district were sometimes buried for months, even for years, and when disentombed, infection broke out anew. Scarlet fever germs, diphtheria germs, may be conveyed from one person to another through dress or books or contact, or they may simply float to and fro in the air, waiting to find a victim. Some allusion has been made earlier to the dangers of great masses of decaying vegetation. The miasma or malaria of marshy lands is only too well known to travelers. Much mystery still hangs about the matter. That a close connection does exist between marshlands and certain diseases in warm climates is undeniable, while the exact nature of the connection is not so clearly understood. Decaying vegetation gives off certain gases, including carbonic acid gas, but though the latter may suffocate a man, it does not bring on intermittent fever, nor do any of its companion gases, released at the same time. The miasmata poured forth by decomposing vegetable matter are minute living disease germs, which, carried by the air, fasten on human beings and lay them low. A certain amount of heat and of moisture are generally counted needful for the development of the poison, yet sometimes it is poured forth from underground dampness through cracks in a dry and hardened earth. If no cracks exist, the miasmata are imprisoned by the hard crust. Again, if the dampness is so excessive as to cause a sheet of water over the surface of the ground, the water acts as a guard, preventing the escape of the germs. These germs of disease, when free, we are told, may be carried on the pollen of marsh flowers or on cryptogamic dust along the valleys or up the mountain sides. Just as ordinary dust drifts into places here and there, leaving other parts free, so does the disease-laden dust settle in favorable spots. And again, in the vapors of the night, in the dews of the morning, the germs of the disease maintain their vitality, and in the sultry breeze may be disseminated far and wide. They are seldom known to ascend above 1,500 or 2,000 feet, and their spread is checked in a remarkable manner by trees, or indeed by any substantial obstacle. Commonly they do not invade large cities, but to this rule there are exceptions. The Campagna di Roma is famous for its terrible malaria. Evil vapors arise from the ground, especially near the lake of Solfatara, and in the heights of summer malignant fevers are so rife as to make the whole Campagna a dangerous place of residence. Many of the country people then flee to Rome, though that city does not escape occasional visitations of malaria fever. Probably the destruction of surrounding woods has made matters far worse than some centuries ago. Travelers in malarious districts should never leave their houses till the morning fogs have melted away, or stay out of doors when the evening mists begin to form. Many an Englishman, impatient of restraint and unbelieving as to the need for care, has fallen a victim to the neglect of this simple rule. Thus we see that the air which brings us so many good things brings us sometimes bad things also. There can never in this world be a power for good which is not also a possible power for evil. That which tells one way beneficially will always tell the other way hurtfully. When a gentle old lady, recommending her pet medicine to all her friends, says, "It may do you good and it can't do you harm," we know that she is declaring an impossibility. That which cannot do harm, if such a thing exists, is of necessity no less incapable of doing good. Air carries injurious dust, noxious gases, germs of putrefaction and disease, this is true. Yet mainly on the whole, those things which the air bears upon its broad wings are for the benefit of living creatures. If we wilfully place ourselves in the path of evil things, they will be brought to us, but if we take reasonable precautions, if we give the air liberty to act, they will as a rule be borne away. There is no purifying power like that of the free wild breezes. Shut up on stagnant air is another matter. A common dust mote remains for years, even for centuries the same. It may stick to some other body, or become detached from it, but in itself it does not change, it cannot grow, it never gives birth to another dust mote, it has not the mysterious gift of life. And the living never springs from the not living. We have around us a world of life, also a world of lifelessness. The two are utterly divided, absolutely apart. That which has not life cannot give birth to that which has life. For a long while this was doubted. Time after time vegetable substance was hermetically sealed in a vessel, which was then so heated as to kill, it was supposed, every kind of living thing within. Yet, weeks later, when the vessel was opened, living germs were there. So it was concluded they must have somehow sprung to life from unliving matter. But now we know that these tiny air and water germs will live through enormously greater heat than was once believed possible. The germs, found alive when the vessel was opened, were simply the descendants of earlier germs not killed by the heat. Closed vessels containing a vegetable solution have since been subjected to greatly increased heat, and when after a while they were opened, no living things were within. All the germs had been killed, and so no fresh forms had sprung into existence. There is a wonderful demarcation between vegetables and animals, yet the two worlds of vegetable life and animal life have each a gentle slope leading down to the margin of the other. On the margin creatures are found which may equally well belong to either side. No such gradual slope, no such doubtful belt appears to divide the world of life from the world of lifelessness. A sheer gulf separates the two. That which has life gives birth to that which has life, but the living never springs from the not living. However low and small, however wanting in organs and powers, certain live things, such as the germs of the air, may be, they are cut off by an impassable chasm from the world of inanimate matter, the world of rock, stone and metal, of water and of air. True, the not living materials pass into and out of the bodies of the living. True, air and water, carbon and oxygen, have a share in the building up of living structures. True, man and beast are literally made of dust and water, so far as the physical frame is concerned. Dust thou art, and unto dust shalt thou return, was no mere figure of speech as uttered unto man. But life is not in the dust, not in water, not in air. Man is largely made of carbon, and a diamond is formed of the same. Yet in the one we have the presence of life, the command of a controlling will, the ever-present joy or pain of consciousness. In the other we find no life, no will, no consciousness. None can bridge the gulf between the two. None can breathe the breath of life into lifeless matter, save he who is the life. End of chapter 34. Chapter 35 of The Ocean of Air, Meteorology for Beginners. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. The Ocean of Air, Meteorology for Beginners by Agnes GIBERNE. Chapter 35 Insects of the Air. From countless myriads of invisible germs, floating and multiplying in air and water, we pass upward to higher and more complex beings, the winged insects of the atmosphere. The ocean of air is an ocean of life, teeming with creatures that breathe and move. These are of all kinds. Grade by grade, from the lowest microscopic organisms, they rise in a steady progression, through creeping and fluttering things innumerable, till higher stages are reached. The insects of the air, multitudinous forms of life are included in this term. Insect is a word often used loosely, often wrongly applied. Spiders are commonly called insects, yet really they are nothing of the kind. The same mistake is made about woodlice, centipedes, and other creatures. A true insect, among diverse characteristics, must always be divided into three parts, the head being so far separate as to move independently of the body. It must also have 6 legs and 2 antennae or feelers. It must breathe by means of air tubes instead of lungs. It must pass through a succession of changes, leading on to the perfect winged state. A spider has 8 legs instead of 6, so it cannot be an insect. Also, if you examine a fly and a spider, you will see at once how freely the fly can turn and twist his little head about, while the spider's head is part of his body. The breathing tubes of insects are very curious. They are made of an exceedingly thin membrane of skin, and they are kept in shape always open for the passage of air by a kind of stiff thread, like very fine wire, wound in close spirals within the tubes throughout their whole length. These tubes pervade every part of an insect's body, even the legs and feet. The smaller tubes run into bigger ones, and the biggest lead to little openings or holes in the sides of the insect, through which air passes in and out. Insects can no more live without plenty of oxygen than men can. To give in a single chapter any full details of the enormous hosts of winged insects which throng the ocean of air is a simple impossibility. Their names alone in a dry monotonous list would far overflow the space I have to spare. Chapters might be filled with short descriptions of British varieties, letting alone those of foreign lands. But to see the insect in its full power and beauty, as well as in its full unpleasantness, one must journey towards the tropics. The mosquito misery is pretty well known to all travelers in South Europe at certain seasons of the year, as well as to all dwellers within the tropics. Anglo-Indians are apt to wax eloquent describing past wakeful nights, vain hunts after a vanishing foe, frantic endurance of a shrill unquenchable buzz, and spotted swollen faces for many a day following. Yet the mosquitoes have their use. Devouring travelers is not the normal occupation of the mosquito. Footnote: E. G. Wood. The greater number of facts in this chapter are culled from his delightful insect volumes. End of footnote. It is merely a little passing entertainment, belonging to its last and highest stage of existence. Before becoming a perfect insect, the mosquito dwells under water as a grub or larva, and there it feeds vigorously upon minute specks of decaying substance, thus helping to render the water pure. Of all insect pests, none is greater than that of the locust, a creature seldom met with in England. Some few locusts appear perhaps every year, but many reported as such are really some other insect, mistaken for the distinguished foreigner. In hotter lands, the migratory locust is a fearful scourge. When once the warning signs are noted of the coming peril, no human power can avert it. Nothing but a change of wind is of any avail. Where the air currents flow, there the locusts go, helplessly, and as if without will of steerage power. Countless hordes of brown creatures darken the atmosphere. Opposition seems useless, for nothing turns them aside. Brushwood over a wide track is set blazing, and still the mighty swarm sweeps by, myriads upon myriads dying in the flames, while yet the army as a whole seems undiminished. I have spoken of their advent as a peril, and so indeed it is, not directly but indirectly, a peril to human life. For when once the locust army settles, the country around is doomed. Grain, fruit, vegetables, leaves, flowers, all are ruthlessly devoured. A visitation of locusts in the east means a famine to follow. Cattle die for lack of food, so meat as well as corn and vegetables fail. Parts of southern Europe have often suffered from locusts, but it is in Asia and Africa that they are seen in fullest force. One vast array of Indian locusts extended in length to no less than 500 miles, and as the swarm flew by, the air was so darkened that big buildings only 200 yards off were almost blotted out. Other insect plagues might be mentioned also. There is the fly torment of a hot summer and of tropical climates. There are wasp torments, cockroach torments, spider torments, the worry and distress to human beings of almost any kind of superabounding insect. More serious pests than these exist in such creatures as the famous tsetse fly of Africa, which exterminates with its deadly sting all large quadrupeds throughout the district where it lives. If ever the tsetse makes its way to British shores, and finds British air to agree with its constitution, then good-bye to our flocks of sheep, our herds of cattle, our fine breeds of horses. Not one of them could stand against the tsetse. Among the fairer and more innocent creatures which float through the blue depths over our heads, the short-lived mayfly is perhaps one of the most abundant. As a perfect insect, it lasts commonly but a few hours. Since no food is needed for so short an existence, it has no mouth. The brief span is passed in a merry, though monotonous dance upon the summer air. In some parts of Europe mayflies have multiplied to such an enormous extent that their little dead bodies have been gathered into piles and used for manure. Dragonflies, often called horse stingers, are most harmless creatures so far as quadrupeds and men are concerned. The idea that they possess stings is a popular delusion. The long, quivering bodies are powerless to do an injury, and if they could bite, they do not. No doubt, in the insect world a different tale would be told, for the dragonfly is a ferocious wild beast, a veritable dragon there. In all the different stages of its existence he is voracious to a degree, and in the latest full-blown stage he is as ready to make a meal of spiders and centipedes as of smaller insects. One African dragonfly is bright red in color, with brilliant opal-hued eyes. Another, a native of India, has brown upper wings, the other two being of vivid metallic green. Again, a dragonfly of Borneo possesses wings crimson blue and green, according to the lights in which they are viewed. Even in England we have a kind, the wings of which glitter, with iridescent hues of metallic purple, green, blue, and gold. It is a pity that all these radiant colors fade after death. Many insects are helpless in a strong breeze, but the powerful wings of the dragonfly, beating the elastic air, are equal to this emergency. Like a vigorous rower delighting to make way against a rapid stream, the dragonfly seems to rejoice in mastering the wind. A remarkable piece of mechanism exists in the wing of the dragonfly. We all understand how a rower makes his way. With the stroke that sends him forward, he presents the breadth of his oar to the water, so as to have a strong pull against it. Then instantly he feathers his oar, letting the water resistance act only on the edge of the blade. But with the vigorous strokes of a dragonfly's wing, how is it that the upward stroke does not exactly neutralize the downward stroke, so as to keep the insect just moving to and fro in one place? Simply because they are not mere up and down strokes. By a wonderfully delicate mechanical arrangement, a kind of little muscular spring, the wings are feathered with every upward stroke. The downstroke makes full use of air resistance to send the insect darting forward, but in the upstroke the edge of the wing slips through the air, meeting with slight opposition. Insects in general do not merely float on the air like balloons through excessive lightness. Most of them are so light and weak that a breeze sweeps them away, yet each has its own weight, and each in perfectly still air would sink to the earth, but for the rowing action of its wings. A common housefly beats the air about 600 times each minute, thus making a continuous humming sound. Without some degree of weight there cannot be real flight. The helplessness of locusts in their migrations has been mentioned earlier. They do not fly like dragonflies against the wind, but are swept along by it. Locusts generally are not good for much in the way of flight. When about to depart on a long aerial journey, they make preparation by blowing themselves full of air. Footnote. From Professor Duncan's Transformation of Insects. End of footnote. So full that the air tubes of their bodies, generally flat, bulge out and become rounded. This makes them lighter than usual to begin with. Then, the exertion of flying heats their bodies, and the air in the air tubes grows warmer, therefore lighter. The locust thus really does float partly, through lightness as used wrongly to be supposed of all flying creatures. But the very fact that it does so makes it to some extent like a balloon, the mere sport of the winds. We have in England some insects which can fairly compete in appearance with their brethren of foreign lands, but it is not so with butterflies. Think what our world would be without flowers or butterflies, without fair ornaments of the earth and of the air ocean. Certain unlovely insects help to purify the physical atmosphere, but beautiful things, such as flowers and butterflies, help to soften and purify the mental atmosphere. Is one more needful than the other? Butterflies in countless varieties are known to us, from the tiny blue thing skimming over English meadows to its splendid cousin of the Himalayas, with radiant-tailed wings peacock-marked in shaded blue and green. One exquisite native of tropical America, we are told, seems to partake with the gems the full glory of color. It is scarcely possible to conceive of a living creature that can surpass this insect in absolute magnificence. The upper surface is radiant azure, as if composed of a sheet of thin mother-of-pearl. When the light falls in the right direction, the color is so intense that the eye can scarcely endure its radiance. And again of another we learn, the upper surface of this butterfly is rich shining opaline blue, with a decided dash of green in some lights. The wings are edged with a broad band of black, in which is a row of little white spots. Another fine creature found in South America is known as the owl butterfly. It is very large in size, the wings being on the outside a chocolate brown, shot with blue and green. The curious part of this butterfly is the under view. There, when the wings are well opened, a distinct and remarkable picture of an owl's face is seen. The general surface is dun-colored with brown mottlings. In the center of each lower wing is a painted eye, and the body of the butterfly serves perfectly for a beak. A preserved specimen of this creature is, or was recently, to be seen at the Crystal Palace. I can vouch after sight for the striking resemblance to the face of an owl. The dead-leaf butterfly is a no less singular instance of imitation in form, so often seen among insects. This kind belongs to the Himalayas, though found elsewhere also. When open and in the act of flight, there is nothing unusual about it, but when the wings are closed and the animal is still, there is every appearance of a dead leaf, brown and veined. A dried specimen in a glass case sent home years ago from India has drawn often the remark from a passing observer, "Why, you've got a dead leaf in there!" A very different kind of insect from the butterfly displays the same tendency to imitation in appearance. I mean the walking stick insect. Some creatures of this kind are the most complete copies of dried sticks, and certainly are more curious than beautiful. They are among the largest known insects. One variety is as big round as a man's thumb, and when its legs are outstretched it is 15 inches long. Another, found in New Guinea, has hind legs, the thighs of which are half an inch thick and over an inch and a half long, while its eggs rival those of a hummingbird in size. It has big scratching body thorns or spikes, and sharp leg prickles. On the whole, One would prefer not to come across any such monster insects in our English woods or meadows. End of chapter 35. Chapter 36 of the Ocean of Air, Meteorology for Beginners. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. The Ocean of Air, Meteorology for Beginners by Agnes GIBERNE. Chapter 36 Birds of the Air. The birds of the air, how natural an expression it seems. We talk of the birds of the air involuntarily, as of the fishes of the sea and the beasts of the earth. Practically, as more than once stated before, all living creatures are creatures of the ocean of air. Since all breathe air, none can live without air. But the birds, living on the very wings of the wind, delighting to soar into highest regions of the atmosphere, are in the fullest sense inhabitants of the air. Birds do not merely float on the air any more than do insects. No insect even is lighter than perfectly still air, and no bird exists which is not very much heavier than air. A balloon floats because of its lightness, and so becomes the helpless sport of the air currents. A bird can resist and struggle against the wind. True, birds are light in make, with hollow air-filled bones. If not so, each bird would need much longer wings and much stronger muscles than are now necessary. But its weight is shown by the fact that if wounded and disabled when flying, it at once falls to the ground. A bird actually lighter than air would float still, even when wounded. Since it keeps itself up through active exertion, it drops when active exertion becomes impossible. When a man rows himself over a lake, he is not merely floating. The boat does float, but it does not advance by means of buoyancy. The man propels the boat by using the resistance of the water. He pushes the boat forward by pushing against the water. A bird does this and more. The bird not only rows itself forward, but also raises itself upward and keeps itself aloft by actual force. A bird's flight is a question not of lightness, but of force against force. It uses the resistance of the air, as the rower uses the resistance of the water. No bird could fly in a vacuum, even if it could live there. The wings would have nothing to push against. Wing movement is often extraordinarily rapid. Even the heavy, slow heron flaps its great pinions at a rate of 130 or 40 strokes each minute, twice that if we count the upward as well as the downward motion. Small birds, particularly pheasants and partridges, vibrate their wings with such speed as to leave only a blurred impression on the eye. In other words, each flap remains upon the retina of the eye until the next comes to mingle with it. A bird is actually forced forward by the elasticity of the air. Like water, only to a greater extent, air may be compressed, but there is always in both fluids a quick rebound or reaction. The wings of a bird striking downward compress the air sharply, and the instant expansion of that compressed air drives the wings on, sending the bird with them. For this purpose the wings are both strong and light in make. They are also joined to the body at such an angle that each stroke necessarily sends the bird forward. A bird cannot fly backward, for the whole set of the wing and the wing feathers is against such a motion. It may drop backwards, yielding itself to the influence of gravitation and only guiding or steadying itself by wing movement, but actually to fly backwards is an impossible feat. Nor can it rise upward except head foremost. Merely to float upwards in any sort of position is again beyond its power. The first rising from the ground implies a certain amount of vigorous exertion, which in the case of very large and heavy birds becomes an actual struggle. Once aloft and under way, they sail onward easily enough. The same difficulty which we saw wonderfully met in the case of the dragonfly recurs here. If each downward stroke of the wing forces the bird onward, how is it that each upward stroke does not undo the work of the last downward stroke, forcing the bird equally far backward? In a bird there is no curious mechanical arrangement for feathering its feathered oars at every stroke. One answer has been given already. The set of the wings altogether is such as to render forward motion easy, backward motion difficult. Also, a bird's wing is rounded or convex on the upper side, hollow or concave on the under side. By the downward stroke it encloses and compresses air vigorously, while in the upward stroke air flows over the edges and escapes all ways. Moreover, a beautiful contrivance is seen in the arrangement of the feathers. They are made so to underlap one another, that when the downward stroke takes place, the compressed air below forces them into a more compact shield, through which little or no air may pass. But when the upward stroke takes place, a precisely opposite effect is seen. The feathers then open and part asunder, and the air streams freely through. Who does not see a mighty mastermind at work in all these wondrously delicate adjustments of nature? Who will not if he will? Birds do not always fly with quick and vehement wing vibration. Sometimes, seated by the sea, one might say a grey and white seagull lying calmly on the air, its heavy white waxen body floating apparently like a feather, with outstretched wings scarcely stirring. This is a feat in which some birds are very much more expert than others. In an absolutely still atmosphere it would not be possible, but air, as we have found earlier, is seldom if ever absolutely still. The effects of wind may be produced in two ways, either by the air flowing against motionless objects, or by objects moving through motionless air. Now here is a practical carrying out of that principle. A bird keeps itself aloft by striking its wings against the air, so using air resistance to overcome the gravitation which drags it earthward. But suppose a wind is blowing against the bird when it is aloft. If the bird is sufficiently dexterous, it may so use the resistance of that moving air against its outspread wings, placed at a certain angle, as to overcome the attraction of earth, and yet to remain still. It is a most delicate and scientific operation, and many birds are incapable of attempting it. The kestrel, as well as the seagull, is an adept at such soaring, and so also is the mighty albatross. Those who have seen the albatross, writes the Duke of Argyll, (Footnote: From the Reign of Law), have described themselves as never tired of watching its glorious and triumphant motion. Tranquil its spirit seemed, and floated slow, even in its very motion there was rest. Rest, where there is nothing else at rest in the tremendous turmoil of its own stormy seas. Sometimes for a whole hour together this splendid bird will sail or wheel round the ship in every possible variety of direction, without requiring to give a single stroke to its pinions. Those long, slender wings, some 15 feet across from one extreme tip to the other. Such wings are peculiarly adapted for flying long and far, for floating at ease, and for overcoming the force of ocean gales. Short-winged birds may advance fast, but they cannot keep it up long, and floating on the air at ease is out of their power. When one thinks of bird life in general, with all its infinite shades of variety, the difficulty is to know what to select for a few paragraphs on the subject. Bird kinds count by thousands and tens of thousands. Bird ways are as varied as human ways, not to say more so. Taking Britain alone, birds pass downward in gradual progression from the great eagle to the little wren, numberless multitudes lying between. Taking the world generally, the list, already so long, is tremendously extended. For then the range extends from the huge, ungainly ostrich to the tiny, brilliant hummingbird. Where the more temperate climates of Earth are found, each season brings its own peculiar phase of bird life. This is markedly the case in England. Winter means commonly for birds an uncertain wandering existence. They have to be very much on the tramp in search of food, except where they find attainable stores, or better still, kind human friends to scatter crumbs day by day. A long and hard frost tells severely upon the birds of the air. Heavy snowstorms break through all their usual habits, slaying large numbers, driving oceanic birds inland, making shy ones tame and wild ones almost domestic. Sea gulls have been seen as high up the Thames as Westminster Bridge, and even the distant dignity of the eagle is not always proof against intense cold. Some years ago, when I was with friends in Scotland, we came across a worthy Highland cottager living in a lonely spot not far from the Dee. She described a long and bitter winter in terse terms, and told how the very eagles had come down from the mountain retreats to hover round her cottage, looking out for scraps of food. River-haunting birds, whose food lies under water, are among the worst off at such times. A sheet of ice means starvation to many a lovely blue and green kingfisher, sitting forlornly among the ice-clothed bushes, vainly watching the hard surface which his beak cannot penetrate. Coming spring works a wonderful change in the world of bird life. Spring is the time for all their pretty love-making and mating, for any amount of singing and quarrelling, for diligent nest-building and egg-laying. The rooks are hard at work, and the sound of the cuckoo is heard, while the woods and meadows ring with the wild sweet voices of thrush and blackbird, linnet and robin. For of course the robin sings still, as he has bravely done all through the winter cold, only he is now part of a general chorus, not one among a very few solos. Then, too, the winter absentees begin to return. The tiny willow wren steals silently back from his winter retreat in Africa, and the swallows and martins troop homeward by no means silently. Some repair their old nests, and some build new ones. The nests are various in kind as the builders, delicately finished constructions here, rough piles of sticks and moss there. Summer comes next, a time of calm happiness to birds, only broken in upon by the inevitable trials of domestic life, by strong weather, and by the attacks of the strong upon the weak. In certain other lands little birds have been almost exterminated, but in England they still spend in the main joyous summer days, and insects have not yet a chance of overwhelming the farmers for lack of birds to feed on them. Birds' voices wane as summer goes by, and little families are launched in life, and arrangements for autumn gradually begin to take shape. The migratory birds draw more together, as if disposed to talk over their plans. Autumn is the time for change, except with those little constant birds who cling faithfully to home through all, taking their chance of ice and snow and bitter blast. Both late summer and early autumn are a quiet, not to say a depressed, time in the bird world, for molting takes place, and singing voices have vanished, and bird powers generally are at a somewhat low ebb. When molting is over, the robin gets back his voice, and also do the wren, the skylark, and a few others. But the autumn singing, however sweet, never approaches the outburst of sound which belongs to spring. Even home-staying birds are very busy, seeking winter retreats, and those who have a long aerial voyage ahead are in all the flurry of a speedy departure. Many people can never travel without a certain amount of preliminary fuss, and birds seem to follow the same rule. After all, no wonder a perilous route lies before them. Migration of birds is beset with many dangers and difficulties. Birds often lose their way, a contrary wind or a spell of dark cloudy weather appears to disorganize their movements, and like mariners without a compass, they are at a loss which direction to take. Footnote from C. Dixon. End of footnote. The wonder seems to be not that they often lose their way through the trackless depths of the air ocean, but that they ever find it. How far they journey by instinct, and how far the younger birds are guided by the knowledge of older ones, who have travelled the same route before, who shall declare with certainty? Strange sights are sometimes witnessed in an autumn evening by the men of a lighthouse. Generally, the migratory companies of birds alight to roost and sleep as night approaches, but sometimes a dark cloud shutting off the daylight with suddenness takes them by surprise, and the gleams of the lighthouse lamp draw them out of their paths, causing further confusion. At such a time myriads of birds may be seen to pass, ducks and swallows, geese and wrens, finches and herons, swans and larks, these and others intermingled with birds of prey, forgetting to prey, while their usual victims forget to flee from them. All alike are bewildered, frightened, hurrying to and fro, wandering hither and thither, not knowing whither to turn. Too many dash out their brains against the strong glass of the lighthouse, and so never even make a fair start for the southern land, whither they are bound. Yet out of all the perils which they meet, great numbers do arrive safely, and great numbers do come back again to us next spring for fresh singing, mating, nest building, and family rearing. It has been lately asserted that no less than 90 varieties of birds may be seen in London alone, not counting escaped foreigners from cages. Rookeries still exist there, and even owls are to be found within metropolitan limits. Jackdaws are tolerably common, the blackbird and the thrush are not absolute strangers, swallows fly to and fro, though they will not build in the great city, and while the redbreast eschews London streets, it still clings to the outskirts. The London birds par excellence are sparrows and pigeons. Before the days of electric telegraphs, the pigeon was the usual news carrier. One well trained will fly at the rate of a mile a minute, keeping up the speed persistently for 100 miles. Marvelous as it sounds, it is exceeded by other birds. A rook, going at full speed, beats the fastest express train ever made by man, or he can hasten through the ocean of air at the rate of 100 miles an hour. The length of time that some birds can fly without needing to alight is extraordinary. Seagulls have been known to accompany steamers all across the Atlantic Ocean, careless of the roughest headwinds, floating about with most absolute ease and apparent absence of exertion, scarcely seeming ever to rest. They are said to sleep upon the wing, tucking away their heads like a canary on its perch, rocked on the bosom of the wild winds, flying in sleep, as we all breathe in sleep, unconsciously and mechanically. From the wide world of bird life we might pass onward still, through multitudes of small and great beasts, till another wide gap is reached, that which divides brute life from human life, that which separates the most highly developed intelligence of lower animals from the wonderful brain and spirit powers of man. Even man, however, head as he is of the animal kingdom, unutterably superior to the noblest of his subjects in possibilities, if not always in action, even he in this life can but creep about, on or near the bottom of the aerial ocean, even he can but watch from thence with curious eyes the wonders of that ocean, searching into its make, its movements, its governing laws, its conflicting forces, its countless forms of life. End of chapter 36. End of The Ocean of Air, Meteorology for Beginners by Agnes GIBERNE.